You might think you understand what darkness means. Empty space, the absence of light, perhaps a quiet void where nothing much happens. But in the deepest reaches of the universe, darkness takes on a different character, entirely. It becomes a presence so massive, so influential, that it can bend the very fabric of space and time around itself. Reality, as it turns out, isn't as simple as we once believed. For centuries, scientists have been surprised to discover that the most powerful forces in the cosmos are often the ones we cannot see directly. The invisible shapes the visible in ways that challenge our most basic assumptions about how things work. We'll be exploring this topic in more depth in this video and learn more about what these cosmic giants really mean for our understanding of the universe. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. When we peer deep into the cosmos, we encounter objects so massive, so quietly influential, that they reshape our understanding of what big actually means. There is something profoundly humbling about contemplating the largest black hole ever discovered, a cosmic entity that sits in the darkness, pulling galaxies into elegant dances they never chose to join. Black holes don't announce themselves with fanfare or bright lights. They exist as invisible architects of the universe, sculpting space itself through pure gravitational influence. The largest ones, these supermassive giants, anchor themselves at the centers of galaxies, including our own Milky Way, where they maintain a kind of cosmic order that has persisted for billions of years. Size, in the realm of black holes, takes on an almost philosophical dimension. We measure their enormity not by any surface we could touch, but by an invisible boundary called the event horizon. This is where the rules of our everyday experience break down completely. Beyond this line, not even light, the fastest thing we know, can escape the gravitational embrace. TON 618 stands as one of the most remarkable examples of cosmic excess we've ever identified. This quasar, located billions of light years away, contains a black hole so massive that it challenges our models of how such objects can even form. Its mass exceeds our Sun by tens of billions of times, creating an event horizon so vast that it could swallow our entire solar system and still have room for countless more. The light we detect from TON 618 began its journey toward us when the universe was much younger, carrying information about conditions that existed long before Earth formed. This distant beacon feeds voraciously on surrounding matter, heating the material to millions of degrees as it spirals inward. The process creates some of the brightest objects in the universe, visible across cosmic distances that strain comprehension. What fascinates astronomers about such massive black holes is the timeline problem they present. Growing something this large requires enormous amounts of time, material, and very specific conditions. The universe, while ancient by human standards, may not have provided enough time for conventional feeding processes alone to create such monsters. Galaxy mergers play a crucial role in this cosmic growth story. When two galaxies collide, their central black holes don't immediately crash together. Instead, they perform a gravitational ballet that can last hundreds of millions of years. As they spiral closer, they disturb vast clouds of gas and stars, funneling material toward the center and setting up conditions for dramatic growth. The merger process itself releases energy in ways that were purely theoretical until recently. Gravitational waves, ripples in the fabric of space-time, carry the signature of these cosmic collisions across the universe. We can now detect these waves with sensitive instruments on Earth, giving us front-row seats to events happening billions of light-years away. Each successful merger adds mass to the growing black hole, but it also creates periods of intense activity. The combined object settles into a new configuration, often with renewed appetite for surrounding material. Over cosmic time, through repeated mergers and steady feeding, certain black holes achieve masses that push the boundaries of what physics suggests should be possible. The environment matters enormously in creating these giants. The largest black holes tend to form in galaxy clusters, crowded neighborhoods where hundreds of galaxies interact over billions of years. These regions provide both the raw material and the dynamic conditions necessary for extreme growth. Dense concentrations of dark matter, that mysterious substance we can detect but don't yet understand, may also play a role. Dark matter provides the gravitational scaffolding that helps ordinary matter clump together, potentially feeding the early growth of what will eventually become supermassive black holes. Temperature paradoxes emerge when we study these objects closely. The black holes themselves are among the coldest things in the universe, with temperatures approaching absolute zero. Yet the material falling into them becomes some of the hottest matter we know about, reaching temperatures that exceed the core of any star. This contrast speaks to something profound about how the universe operates. The most extreme cold and the most extreme heat exist in intimate proximity, separated only by an invisible boundary that defines the edge of our observable reality. Detection of these cosmic giants requires detective work on a scale that spans decades. Astronomers look for telltale signs: the way nearby stars orbit unusually fast, how light bends around invisible masses, or how jets of material stream away from regions that appear empty in optical telescopes. Radio telescopes pick up signals from the heated material surrounding black holes, while X-ray detectors identify the high-energy radiation produced as matter accelerates to incredible speeds. Space-based instruments provide views unfiltered by Earth's atmosphere, revealing details that ground-based observations might miss. The data often comes in fragments, pieces of a puzzle that scientists assemble over years of careful observation. Confirming the mass of a supermassive black hole requires multiple independent measurements, cross-referenced with theoretical models that themselves continue to evolve. Recent discoveries have pushed the boundaries of what we thought possible in the early universe. Black holes with billions of solar masses apparently existed when the cosmos was less than 1 billion years old, challenging our understanding of how quickly these objects can grow. Some theories suggest that the first black holes formed directly from the collapse of primordial gas clouds, bypassing the usual stellar formation process entirely. These seed black holes might have started much larger than those formed from dying stars, giving them a head start in the cosmic growth race. Alternative formation mechanisms continue to emerge from theoretical research. Perhaps multiple smaller black holes merged rapidly in the dense early universe, or maybe different physical processes operated when the cosmos was young and more compact. The philosophical implications ripple outward from these discoveries. If the largest black holes formed when the universe was young, they serve as anchors for everything that came after. Galaxies, stars, planets, and eventually life itself all evolved within gravitational frameworks established by these ancient giants. We exist in a universe shaped by objects we cannot see directly, influenced by forces that operate on scales our minds struggle to grasp. The largest black hole sits in its distant galaxy, quietly maintaining the cosmic order that made our existence possible, yet remaining forever beyond our direct reach. When matter spirals toward these cosmic giants, it creates something like a luminous whirlpool in space. The material heats up as it falls, glowing so brilliantly that we can detect this light from distances that span most of the observable universe. It's a strange thought, really, that something defined by its darkness becomes visible through the very matter it consumes. The numbers behind these objects stretch our understanding in peculiar ways. Take the black hole at the center of TON 618, a quasar that sits more than 10 billion light-years from Earth. Its mass equals roughly 66 billion of our suns combined. Our own sun already holds 8 planets in its gravitational embrace, along with countless asteroids, comets, and distant icy bodies that drift in the outer darkness of our solar system. Imagine multiplying that gravitational influence by 66 billion. The event horizon of such a monster would extend far past Neptune's orbit, reaching into the distant regions where our solar system gradually fades into interstellar space. Yet even this unimaginable scale becomes humble when placed against the backdrop of an entire galaxy, which can stretch across hundreds of thousands of light-years. There's something quietly profound about this contrast. We discover the largest black hole known to science, an object so massive it defies our everyday sense of scale. But in the cosmic architecture around it, this giant remains just one component, one player in a much grander system of stars. gas, and dark matter. The light we observe from TOM 618 began its journey when the universe was significantly younger than it is today. We're essentially looking backward through time, seeing not what this object is now, but what it was billions of years ago, long before Earth had even formed from the swirling dust around our young sun. This temporal distance raises fascinating questions about the early universe. How did such enormous concentrations of matter come together so quickly, in cosmic terms? Were there special conditions in those ancient epochs that allowed these giants to grow at unprecedented rates? The answers remain elusive, hidden in regions of space and time we're only beginning to explore. Measuring something so distant and massive presents its own set of challenges. We cannot send probes or place these objects on scales. Instead, astronomers rely on the behavior of light and the motion of nearby matter. They study how fast gas and stars orbit around galactic centers, using these velocities to calculate the gravitational forces at work. For distant quasars, scientists examine the spectrum of light from the glowing accretion disk. Subtle shifts in wavelength reveal how quickly material moves and how far it sits from the central black hole. These measurements carry uncertainties, margins of error, that remind us how much we still don't know. The title of largest black hole ever discovered remains a temporary designation, more like a placeholder waiting for the next discovery. Somewhere in the vast regions we haven't yet surveyed, even larger objects may be quietly shaping space and time, waiting for our telescopes to find them. This ongoing search carries a certain excitement. Each new discovery adds another piece to the puzzle of how structure emerges in the universe. We're slowly mapping the extremes of gravity, mass and scale that exist in the cosmos. When we talk about the biggest things in existence, we often reach for familiar comparisons. We say a galaxy would take light thousands of years to cross, or that a black hole could swallow our entire solar system. These comparisons help, but they also highlight how limited our everyday sense of scale really is. Our daily lives unfold in rooms, streets, and cities. Even the largest landscapes we experience, mountains and oceans, fit comfortably within a single planet. The universe seems indifferent to our preference for manageable sizes. When you first encounter numbers like tens of billions of solar masses, the figure can feel almost abstract. It's so far beyond ordinary experience that it loses its sharp edges, becoming more of a soft, rounded concept than a precise measurement. Perhaps that's not entirely unfortunate. Maybe part of the wonder lies in letting our minds stretch toward these scales, even if we never quite reach them completely. Darkness takes on a different meaning in this context. On Earth, darkness usually means the simple absence of light, something that comes and goes with the setting sun or the flip of a switch. The darkness of a black hole operates differently. It's not just a lack of illumination, but a region where light itself cannot escape once it crosses a certain boundary. This gives black hole darkness a unique quality, not empty, but sealed. Light represents the fastest traveler in the universe, carrying information across space, telling us about distant stars and ancient events. Yet, there are places where even this ultimate messenger cannot return to share its stories. The event horizon marks this boundary, a quiet line drawn in space beyond which information cannot flow back to the outside universe. But even in these regions of extreme gravity, a kind of balance persists. Black holes don't simply erase their surroundings. Most sit at galactic centers, surrounded by vast, glowing structures of stars and gas. The darkness nests inside light, and these opposites coexist in ways that shape entire galactic systems. It's a reminder that even the most extreme objects in the universe participate in larger patterns of structure and organization. As our telescopes improve and new instruments come online, we continue scanning the sky for signs of these cosmic extremes. Each discovery teaches us not just about black holes themselves, but about the conditions in the early universe, the formation of massive structures, and the fundamental nature of space and time. In a universe that seems to have no obvious edge, what does it really mean for something to be large? And in a cosmos filled with light from billions of stars, what does it mean for something to be truly dark? These questions linger at the edges of our understanding, reminding us that even our greatest discoveries reveal how much mystery still surrounds us. When we picture a black hole, our minds often drift to something like a cosmic drain, pulling everything into an empty void. That mental image captures part of the truth, but it misses something crucial. These objects aren't empty spaces at all. They're more like nature's ultimate compression chambers, where enormous amounts of matter get squeezed into impossibly small volumes. The gravity we feel from a black hole doesn't come from nothingness. It comes from something incredibly dense, incredibly real, even though our eyes can never see it directly. This creates an interesting puzzle about what we mean when we talk about size. The biggest black hole isn't necessarily the widest object you could measure with a cosmic ruler. It's the most massive, the most influential. Think about how a river shapes the landscape around it. Over thousands of years, the water carves valleys, deposits soil, and determines where towns get built. Roads follow the riverbank, bridges span at the narrowest points, and entire communities arrange themselves around this flowing presence. Black holes work similarly in space, but on a scale that makes rivers look like tiny scratches. The largest black holes sit at the centers of galaxies, organizing stellar neighborhoods that stretch for hundreds of thousands of light years. Stars orbit them in careful patterns. Gas clouds spiral inward, creating brilliant displays as they heat up from the friction. Even light itself bends as it passes near these gravitational giants. What fascinates astronomers is how black holes and galaxies seem to grow together, like dance partners matching each other's movements. The biggest galaxies tend to harbor the most massive black holes. Neither one dominates completely, they influence each other's development across billions of years. We detect these invisible monsters by watching their effects on everything around them. Stars move faster than they should if they were only responding to other stars. Gas glows with temperatures that require extreme gravitational forces to explain. Light from distant objects gets distorted as it passes through warped space-time. From these clues, scientists piece together portraits of objects we can never photograph directly. It's detective work on a cosmic scale, following gravitational fingerprints to map the unmappable. Even with our most sophisticated instruments, there's something wonderfully old-fashioned about this process of deduction. The language we use reveals how these discoveries make us feel. We call them monsters, giants, cosmic behemoths. These aren't neutral scientific terms. They're borrowed from human stories, from myths and legends. When we describe something as a monster, we're not just stating facts. We're expressing our emotional response to encountering something beyond our usual experience. That emotional response isn't always fear. Though fear certainly plays its part, there's also fascination, the magnetic pull of confronting something that challenges what we thought we knew about reality. The largest known black hole poses no threat to Earth. It's far too distant for its gravity to affect our galaxy. But it captures our imagination, simply because of what it represents. These objects fit into the universe's larger story of structure and growth. Everything started in a hot, dense beginning, then expanded and cooled. Matter clumped together, under gravity's patient influence. First came basic particles, then atoms, then clouds of gas, then the first stars lighting up the cosmic darkness. Black holes emerged naturally from this process, not as weird exceptions, but as gravity's inevitable conclusion when enough mass gathers in one place. The early universe had different conditions than today. Matter was distributed differently, and the first generation of stars were likely much more massive than typical stars we observe now. When those ancient giants exhausted their fuel and collapsed, they left behind black holes that were already quite large. These became seeds, growing slowly over cosmic time into the supermassive and ultramassive black holes we detect today. There's something comforting about this gradual process, the way the universe builds its most impressive structures, through patience rather than haste. Gas drifts inward over millions of years. Stars form, shine, and die. Galaxies collide and merge in slow-motion ballets that take billions of years to complete. Black holes themselves sometimes spiral together, creating gravitational waves that ripple through space-time. Each individual event might seem unremarkable on cosmic scales, but together they create something truly extraordinary. The darkness of black holes isn't just about light being trapped. It represents a kind of intellectual boundary, a place where our current theories start to break down. Near the center of a black hole, physicists encounter what they call a singularity, where density and gravitational forces become so extreme that our equations can't handle them anymore. This doesn't necessarily mean there's literally a point of infinite density sitting there. It might just mean our models aren't sophisticated enough yet to describe what's really happening. The singularity could be nature's way of telling us we need better theories, more complete understanding of how gravity works at the most extreme scales. In some ways, this intellectual darkness is as interesting as the physical darkness. It marks the frontier of human knowledge, the place where confidence fades into uncertainty. Rather than being frustrating, this can be wonderfully humbling. It reminds us that science isn't a finished collection of answers, but an ongoing conversation with the universe. These cosmic scales might seem completely disconnected from human experience, but there are surprising parallels. We all face moments that feel vast and uncertain, big decisions where we can't see the outcome, periods where the future seems dark, not because it's empty, but because it's unknown. In those situations, we do something similar to what astronomers do when studying black holes. We observe what we can, gather the available evidence, and take careful steps forward into uncertainty. We follow the edges of what we know, slowly expanding the boundary of understanding. The largest black hole we've discovered sits at the heart of a quasar called TON 618. When scientists study this object, they're not just impressed by its enormous mass. They're intrigued by what it reveals about cosmic history. The light reaching us today began its journey billions of years ago, when the universe was much younger. This means the black hole was already gigantic in those early times, which raises fascinating questions about how it grew so quickly. Were there special conditions in its cosmic neighborhood that allowed rapid growth? Did it form through different processes than the black holes we see forming today? These questions push us toward deeper understanding of how the universe evolved from its simple beginnings into the complex structure we observe now. Imagine for a moment that our universe is a vast library filled with countless stories we're only beginning to read. Some of these stories are written in languages we understand, like the gentle pull that keeps our feet on the ground. Others are written in scripts so foreign, so extreme, that we can barely comprehend their meaning. The largest black holes belong to this second category. When astronomers first spotted these cosmic giants, they faced a puzzle that still keeps them awake at night. How does something grow so impossibly massive? We're talking about objects that contain the mass of billions of suns, all packed into a region smaller than our solar system. It's like trying to stuff an entire city into a matchbox, except the city is made of collapsed stars. The mystery deepens when you consider timing. These monsters appear in observations of the early universe, when everything was supposedly young and small. It's as if you walked into a nursery and found a fully grown oak tree among the seedlings. The universe simply hadn't been around long enough for normal growth processes to create such behemoths. This brings us to one of those beautiful contradictions that make science so compelling. The very largest black holes might have formed through the most gentle process imaginable. Picture the early universe as a cosmic soup, smooth and warm. Tiny ripples in this soup, barely noticeable differences in density, began to grow under their own gravity. These ripples were so subtle that if you could have floated there, you wouldn't have felt anything unusual. But gravity is patient, and it compounds. Over millions of years, these gentle undulations became valleys where matter collected. The valleys deepened, drawing in more material, which made them deeper still. Eventually, some of these cosmic valleys became so deep that nothing, not even light, could climb back out. There's something almost philosophical about this process. The universe's most violent objects, capable of tearing apart stars and bending space itself, might have begun as the gentlest of whispers in the cosmic background. It reminds us that small changes, given enough time, can reshape entire realities. Modern telescopes peer across billions of light years, essentially looking back in time. When they spot these ancient giants, they're seeing the universe as it was when it was just a fraction of its current age. The light has been traveling toward us since before Earth existed, carrying messages from a cosmos we can barely recognize. These distant observations reveal something unexpected. The largest black holes seem to have relationships with their host galaxies that follow surprisingly strict rules. It's as if the galaxy and its central black hole are dance partners, each one influencing the other's movements in ways we're still trying to understand. The black hole feeds on gas and stars from the galaxy, growing larger and more powerful. But as it feeds, it also releases tremendous amounts of energy that can heat up the surrounding space, potentially stopping more material from falling in. It's a cosmic thermostat of sorts, regulating its own growth in ways that seem almost deliberate. This self-regulation raises profound questions about the nature of complexity in the universe. How do such intricate feedback systems emerge from simple physical laws? It's like watching a river carve its own banks, creating the very channel that guides its future flow. When we try to wrap our minds around the scale of these objects, normal comparisons break down completely. If you could somehow shrink the largest known black hole to the size of a marble, that marble would still contain more matter than our entire solar system. The gravitational field around such an object warps space so severely that time itself runs differently, depending on where you are. Near the event horizon, that invisible boundary where escape becomes impossible, time stretches like taffy. What seems like minutes to someone falling in would appear as hours to a distant observer. The universe literally becomes a different place, depending on your perspective. This isn't science fiction, it's the strange reality of extreme gravity. These time distortions hint at something deeper about the nature of reality itself. Space and time aren't the rigid stage we imagine them to be. They're more like a flexible fabric that can be stretched, twisted, and folded by the presence of matter and energy. The largest black holes are master sculptors of this fabric, reshaping the very foundations of existence around them. The search for these cosmic giants continues with increasingly sophisticated instruments. Each new discovery pushes the boundaries of what we thought possible. Telescopes planned for the next decade will peer even deeper into space, potentially revealing black holes so massive and so distant that they challenge our current understanding of cosmic evolution. There's a curious comfort in knowing that no matter how much we discover, the universe always seems to have more surprises waiting. Each answer we find opens up new questions, like rooms in an infinite mansion. The largest black hole ever discovered holds that title only temporarily, until the next record breaker emerges from the cosmic depths. Consider the beautiful irony that these objects, defined by their ability to trap light, are often among the brightest things in the universe. As matter spirals into them, it heats up to incredible temperatures, glowing with the fury of billions of stars. They're simultaneously the darkest and brightest phenomena we know of. Another of those delightful contradictions that pepper the cosmos. The gas falling into these giants doesn't go quietly. It forms swirling disks that can stretch across light years, generating magnetic fields powerful enough to launch jets of particles at nearly the speed of light. These jets can extend for millions of light years, carrying energy far out into intergalactic space. It's as if the black hole is broadcasting its presence across vast distances, announcing itself to the universe. The mathematics describing these objects reads like poetry written in equations. The relationship between mass, space, and time becomes an elegant dance of numbers that somehow captures the behavior of the most extreme objects in existence. There's something deeply satisfying about the fact that human minds, evolved on a small planet orbiting an ordinary star, can decode the secrets of such exotic phenomena. These discoveries remind us that we live in a universe far stranger and more wonderful than our ancestors could have imagined. The gentle gravity that holds us to Earth is the same force that creates cosmic monsters capable of devouring entire solar systems. The atoms in our bodies were forged in stellar furnaces, while the space around us is shaped by invisible giants lurking in galactic cores. Perhaps most remarkably, these impossibly distant objects connect us to the deepest questions about existence itself. They mark places where our current understanding reaches its limits, where the familiar laws of physics stretch toward breaking points. In studying them, we're not just learning about black holes, we're probing the fundamental nature of reality, space, time, and the strange, beautiful universe we call home. When we think about the forces that shape our universe, there's something almost deceptive about gravity. It seems so gentle, so polite in our daily lives. You can jump, you can lift things, you can even blow a feather around with your breath. But this gentleness, this apparent weakness, is really just gravity waiting for the right moment to show what it's truly capable of. Picture this: the core of a massive star, maybe 20 times heavier than our sun, has been burning fuel for millions of years. It's like a cosmic furnace constantly fighting against its own weight. The nuclear fires create pressure, pushing outward, while gravity pulls everything inward. For most of the star's life, this is a fairly even match, but nuclear fuel doesn't last forever. When that fuel runs out, something remarkable happens. The core temperature drops, the pressure weakens, and suddenly gravity isn't being polite anymore. It starts to win, completely and utterly. The core begins to collapse, shrinking down, becoming denser and denser. Imagine trying to squeeze all the mass of a mountain into the size of a marble. That's the kind of compression we're talking about. There comes a moment, a specific threshold, where the core becomes so dense that even light itself cannot escape. This is how a black hole is born. It's not a dramatic explosion, necessarily. It's more like gravity finally getting its way after eons of negotiation. The boundary around this collapsed core, what we call the event horizon, isn't something you could touch or feel. Think of it more like an invisible line in space itself. Outside this line, paths still exist that can lead you back to the wider universe. Inside it, every possible path leads only inward towards center. If you somehow found yourself approaching this region, you wouldn't hit a wall. You'd simply reach a point where turning back becomes impossible. Now, here's something that might surprise you. Most black holes aren't cosmic vacuum cleaners, constantly devouring everything around them. Space is incredibly vast, and there's actually a lot of empty room even near a black hole. Objects can orbit them safely, just like planets orbit stars. The key word there is safely, meaning at a reasonable distance. But when something does venture too close, that's when things get interesting. Gas, dust, sometimes entire stars. They don't usually fall straight in. Instead, they begin to spiral around, forming what looks like a flat, spinning disk. The friction in this disk, combined with the intense gravitational forces, heats the material to extraordinary temperatures, hot enough to glow brilliantly. And here's one of the great ironies of the universe. Black holes themselves are completely dark, but the regions around them can be among the brightest places we know of. Some of these glowing disks actually outshine entire galaxies. It's almost poetic, in a way. The darkest objects creating some of the most spectacular light shows in the cosmos. As material continues to fall past that point of no return, the black hole grows. Each bit of mass that crosses the event horizon adds to the total. The more massive it becomes, the larger that boundary grows, the farther its influence reaches into space. In environments where there's plenty of material to feed on, this growth can continue for billions of years. This brings us to something truly staggering. In the centers of most large galaxies, there are black holes that weigh millions, sometimes billions of times more than our sun. These didn't form from the collapse of a single star. They grew over cosmic time, starting from smaller beginnings and gradually adding mass. Think about a crowded room where people are constantly moving around. Sometimes two people bump into each other and end up walking together. In the centers of galaxy clusters, entire galaxies can collide and merge in a similar way. When this happens, their central black holes eventually find each other and begin their own gravitational dance. At first, they orbit at a distance, surrounded by swirling stars and gas. Over time, interactions with this surrounding matter cause them to lose energy and spiral closer together. Eventually, They merge in an event so violent it sends ripples through the very fabric of space itself. These ripples, gravitational waves, spread outward at light speed, carrying information about the collision across the universe. Each merger creates a black hole larger than either of the originals. Over billions of years, through repeated collisions and steady feeding, some grow to truly mind-boggling sizes. We're talking about objects so massive that their influence shapes entire galaxies. Now, let's step back and think about what makes gravity so special. In everyday situations, it's easy to ignore because other forces often dominate. The electromagnetic forces holding atoms together are far stronger on small scales. The structural strength of materials resists compression. Even air pressure can balance gravity, as we see with balloons or clouds floating in the sky. But gravity has one unique advantage: it always adds up. There's no such thing as negative mass to cancel it out. Every bit of matter, no matter how small, contributes to the overall pull. Over large distances and long periods of time, this makes gravity the dominant force shaping the universe. This is why the largest structures in the cosmos, galaxies, galaxy clusters, the web-like patterns of matter stretching across space, are all arranged by gravity, and at the deepest centers of some of these structures, gravity becomes so concentrated that it creates black holes. For the largest black holes, this process reaches an extreme. Their mass isn't just the result of a single collapse, but the cumulative outcome of countless events. Each star that falls in, each cloud of gas that spirals past the point of no return, each merger with another black hole, all of it adds to the total. As these giants grow, they begin to influence their environment in subtle ways. The energy released by their accretion disks can heat surrounding gas, sometimes pushing it away and slowing further growth. The black hole and its host galaxy can enter into a kind of feedback loop, each affecting the evolution of the other. This relationship between gravity, growth, and balance is fascinating to astronomers. These aren't just extreme objects existing in isolation. They're key players in the story of how galaxies form, evolve, and sometimes stop creating new stars altogether. There's also a quieter aspect to gravity's dominance, one that has to do with time itself. Near a very massive object, the flow of time is affected. According to general relativity, gravity isn't just a force pulling on objects. It's a curvature of space and time combined. The more mass you have, the more you bend this fabric of reality. Close to a black hole, this bending becomes very strong. From the perspective of a distant observer, a clock near the event horizon would appear to run slower and slower as it approaches. In a sense, gravity doesn't just win over matter and light, it wins over time itself. This doesn't mean someone falling into a black hole would experience dramatic time changes from their own perspective. Their watch would tick normally for them, but the outside universe would seem to speed up, racing through its future while they approach that boundary. This interplay between gravity and time adds another layer to the idea of winning. It's not just about pulling things inward, it's about reshaping the very stage on which events unfold. There's something almost rhythmic about this story. A quiet beginning, a slow build, a tipping point, then a new state operating under different rules. This pattern appears in many places, not just black hole formation. Stars are born this way. Galaxies evolve this way. Even closer to home, we see it when water freezes, when sand dunes form, when societies grow and change. In each case, small interactions accumulate over time until something entirely new emerges. With the largest black holes, this emergence is particularly striking because it represents gravity at its most extreme. A place where familiar concepts like solid objects, steady light, and regular time give way to something more abstract, more challenging to picture. Yet this extreme outcome still stems from the same simple principle we started with. Things with mass attract each other. That rule, applied over vast distances and enormous stretches of time, is enough to create stars, galaxies, and the most massive black holes we've discovered. The universe doesn't need complicated instructions to build complex structures. It works with a few basic principles, repeated and combined in countless ways. Most of the time, gravity seems easy to overlook, but given enough room to operate, enough time to accumulate its effects, it shapes the largest and most mysterious objects we know of. There's something profound about this. The idea that the gentlest force in our daily experience becomes the architect of the cosmos itself when given the chance to work on the grandest scales. When you look at the grandest things around us, there's often something surprisingly modest hiding at their beginning. Think about it for a moment. Every towering mountain once started as tiny shifts in rock layers. Every rushing river began as just a few drops of water finding their way downhill. The same pattern holds true across the entire cosmos. Those massive spiral galaxies we see in photos, with their brilliant cores and sweeping arms, they all began as barely noticeable differences in how matter was spread around the early universe. Just tiny variations in density, nothing more. Black holes follow this same humble beginning story. The supermassive ones we know about today, these quiet giants that can weigh billions of times more than our sun, they didn't start out that way. They began as seeds, cosmic seeds, if you will. There's something almost poetic about thinking of black holes as seeds. A regular seed doesn't look like much when you hold it in your hand. It's small, easy to ignore, gives you no hint of the massive oak tree or sprawling garden it might become someday. But give it the right conditions, enough time, a steady supply of what it needs, and it transforms into something magnificent. Black holes work in a similar way, just on a scale that's hard to wrap your head around. To understand how they grow from something relatively small into these cosmic monsters, we need to go back to the early universe. We're talking about the first few 100 million years after everything began. The universe back then was a completely different place. Much smaller, much denser, filled mostly with the simplest elements, hydrogen and helium. No heavy metals existed yet, no planets, no complex chemistry, certainly no life. But even in this simple cosmic soup, there were spots where matter clumped together just a little bit more than average. Gravity doesn't care how small these differences are. It started working on these slightly denser regions, pulling more material in, making them even denser. Eventually, this process formed the very first stars. These ancient stars were nothing like the ones we see today. Many were absolutely enormous, far bigger than our sun. Because they were so massive, they burned through their nuclear fuel incredibly fast. Their lives were brief, but intense, ending in spectacular collapses and explosions that spread heavier elements throughout space for the first time. When some of these monster stars collapsed, they left behind black holes that were already larger than most stellar black holes we see forming today. These were among the first seeds, but scientists think there might have been another way to create these early seeds. In some regions of space, instead of forming stars first, huge clouds of gas might have collapsed directly into black holes. These direct collapsed black holes would have started their existence much larger than anything born from a single star. If this process really happened, it would have given the universe a head start in building supermassive black holes. Whether the earliest seeds came from massive stars, direct collapse, or a mix of both, the key point is that they existed in a universe that was absolutely packed with material and activity. Galaxies were forming and merging much faster than they do now. Gas was everywhere. The cosmic environment was rich with opportunities for growth. Once a black hole exists, its main way of gaining mass is through something called accretion. This is basically the steady intake of matter from everything around it. Gas clouds drifting through space get caught by the black hole's gravity. As this gas falls inward, it doesn't usually plunge straight down. Instead, it begins to spiral around, forming a rotating disk. This accretion disk becomes a place of absolutely extreme conditions. Friction between different layers of gas causes everything to heat up, sometimes to millions of degrees. At these incredible temperatures, the gas starts glowing, releasing enormous amounts of energy as light and other forms of radiation. This is what makes quasars and active galactic nuclei so blindingly bright. The black hole itself stays dark, but the feeding process lights up the surrounding area like a cosmic lighthouse. Accretion isn't always smooth and steady though. It can happen in bursts depending on how much material is available and how it's distributed around the black hole. A passing cloud of gas, the destruction of a star that wanders too close, or the merger of two entire galaxies can suddenly deliver a fresh supply of matter to the black hole's neighborhood. When that happens, the rate of growth can spike dramatically, and the black hole can bulk up more rapidly for a while. But there's a natural limit to how fast a black hole can consume material. As the accretion disk becomes brighter and brighter, all that radiation starts pushing outward on the incoming gas. If this outward pressure becomes strong enough, it can slow down or even temporarily stop the inflow of matter completely. This balance between gravity pulling inward and radiation pushing outward creates what's known as the Eddington limit. This means that even under perfect conditions, a black hole cannot grow infinitely fast. It takes time, often hundreds of millions or even billions of years, for a black hole to transform from a seed into a giant. Time becomes one of the most crucial ingredients in this cosmic recipe. The universe is about 13.8 billion years old. That might sound like an unimaginably long span, and it is, but when you're trying to build something that weighs tens of billions of times more than a star, every billion years matters enormously. This is why the discovery of extremely massive black holes in the very early universe fascinates scientists so much. If a black hole is already gigantic when the universe is only a few billion years old, it suggests that either it started from an unusually large seed, or it managed to grow at an exceptionally high rate, or both. As black holes grow, they don't exist in isolation. They're embedded within galaxies, and those galaxies are part of even larger structures like groups and clusters. The growth of a black hole and the evolution of its host galaxy are intimately connected. When a galaxy has plenty of cold gas available, it can form new stars at a rapid pace. That same gas can also feed the central black hole. But as the black hole grows larger and becomes more active, the energy it releases can heat up, or even blow away some of that precious gas. This can slow down or completely shut off star formation in the galaxy. It's like a cosmic conversation between the black hole and its galaxy. The galaxy provides the black hole with material to grow, while the black hole influences how the galaxy develops over millions of years. This ongoing interaction often leads to a delicate balance, where the size of the black hole and various properties of the galaxy become closely related. Observations show us that in many galaxies, the mass of the central black hole correlates strongly with the mass of the galaxy's central bulge of stars. This relationship suggests that their histories are completely intertwined, shaped by the same cosmic processes over vast periods of time. There's something almost beautiful about this cosmic partnership, each component influencing the other's destiny. Another important pathway to growth comes from mergers. Galaxies don't stay neatly separated forever. Gravity constantly pulls them toward each other, especially in dense cosmic neighborhoods where many galaxies cluster together. When two galaxies finally collide, something fascinating happens. Their stars mostly pass by one another without direct impacts because the distances between individual stars are so enormous, but their gas clouds interact violently, compress together, and trigger bursts of new star formation. Meanwhile, their central black holes begin a slow gravitational dance that can last for millions of years before they eventually spiral together and merge into an even more massive black hole. These cosmic collisions represent some of the most energetic events in the universe. Two black holes locked in their final spiral dance represent one of the universe's most profound transformations. As they merge, they create something larger than the sum of their parts, releasing energy that ripples through space-time itself. These gravitational waves carry the signatures of their creators, traveling for billions of years until sensitive detectors on our planet can capture their whispers. Each merger adds another chapter to the story of cosmic growth. Over vast stretches of time, a black hole might absorb dozens, hundreds, or even thousands of companions. The mathematics of accumulation becomes staggering when you consider the timescales involved. What starts as a relatively modest object can transform into something truly colossal through this patient process of consumption and merger. But there's another pathway to enormous size, one that involves steady feeding rather than dramatic collisions. Picture a black hole surrounded by streams of gas, slowly but persistently drawing matter inward. This accretion process can continue for millions of years, adding mass grain by grain, atom by atom. The persistence of gravity creates a kind of cosmic patience that we rarely encounter in our daily lives. The largest galaxies provide the most favorable conditions for this growth. Sitting at the centers of massive galaxy clusters, these cosmic cities contain hundreds or thousands of individual galaxies, all bound together by gravity. The central galaxy becomes a kind of gravitational sink where matter naturally flows inward. Gas clouds, individual stars, and sometimes entire smaller galaxies get pulled toward the center. When we look at the biggest black holes, those with masses reaching tens of billions of times our Sun, we're seeing the end result of this cosmic real estate principle. Location determines opportunity. A black hole that forms in a quiet, isolated region of space might remain relatively small throughout its entire existence. But one that emerges in a dense, active environment has access to seemingly endless supplies of material. The growth patterns reveal themselves when we study these objects across cosmic time. There are periods of quiet accumulation, where the black hole grows slowly and steadily. Then there are episodes of intense activity, when the black hole becomes a quasar, blazing across the universe as it rapidly consumes large quantities of matter. These active periods can outshine entire galaxies, making the black hole visible from billions of light years away. The dramatic moments come during major mergers, when two massive galaxies collide and their central black holes eventually combine. These events can double the mass of the surviving black hole in a relatively short time. Cosmically speaking, the energy released during such mergers creates gravitational waves so powerful they can be detected across vast distances. This alternating rhythm of growth, quiet periods followed by bursts of activity, reflects something deeper about the universe's own evolution. In the early cosmos, when matter was denser and structures were still forming rapidly, black holes had more opportunities for dramatic growth. The universe was a more crowded, more active place back then. As cosmic expansion continues, matter becomes more spread out, and the opportunities for rapid growth become rarer. The largest black holes we observe today are, in many ways, fossils from this more active cosmic past. They preserve the memory of a time when the universe was younger, denser, and more dynamic. Consider what this means for our understanding of cosmic giants. The largest black hole isn't necessarily special because of some inherent property it possessed from the beginning. Instead, it represents the culmination of countless chance encounters, favorable circumstances, and perfect timing. A seed that happened to form in exactly the right place, at exactly the right time, with access to exactly the right resources. This perspective reveals something profound about growth itself. Environmental factors often matter more than initial conditions. The same basic process, beginning with similar starting points, can lead to vastly different outcomes depending on circumstances. Some seeds flourish while others remain modest, not because of fundamental differences in their nature, but because of the opportunities they encounter. The sequence of events matters tremendously. For a black hole to reach truly enormous proportions, certain conditions need to align in the proper order. Early access to abundant gas supplies, timely mergers with other growing black holes, and a host galaxy massive enough to support continued feeding over billions of years. There's a particular black hole associated with a distant quasar that often claims the title of most massive known object of its kind. What makes this discovery so intriguing is that we observe it at a time when the universe was relatively young. This suggests that its growth was both remarkably early and extraordinarily efficient. Such objects challenge our theoretical models of black hole formation and evolution. If current theories cannot account for something so massive existing so early in cosmic history, then those theories need refinement. The largest black holes serve as cosmic benchmarks, pushing the boundaries of our understanding. Scientists continue to debate whether there are ultimate limits to black hole growth. Theoretical considerations suggest several potential constraints: the availability of matter in the surrounding environment, the expansion of the universe itself, and the feedback effects between the black hole and its host galaxy all play roles in determining maximum possible sizes. In a universe that continues expanding and becoming more diffuse, the era of rapid black hole growth may eventually come to an end. The distant future might see these cosmic giants entering a period of slow decline as new material becomes increasingly scarce. But in the present epoch, and certainly in the observable past, growth remains a central part of their story. The largest black holes remind us that even the most extreme objects in the universe are products of gradual processes, shaped by time, gravity, and circumstance. They represent not sudden creation, but patient accumulation across cosmic ages. In their immense masses, we can read the history of structure formation, galactic evolution, and the relentless influence of gravity on cosmic scales. When we think about black holes and their sizes, we enter a realm where our everyday language starts to break down. The word big works perfectly fine for describing a house or a mountain. But when you're dealing with objects that contain the mass of billions of stars, that simple word suddenly feels inadequate, almost fragile. The Sun gives us a good starting point for understanding scale. It contains more than 99% of all the mass in our solar system. You could fit over 1 million Earths inside it if you hollowed it out completely. Its gravitational pull reaches so far that it keeps icy rocks in orbit way beyond Pluto. By human standards, the Sun is absolutely massive. Now, stellar mass black holes typically weigh anywhere from a few times to maybe 50 times what our Sun weighs. They form when individual massive stars collapse at the end of their lives. Here's where things get interesting though. A black hole with the same mass as our Sun would have an event horizon only about 6 kilometers across. That's roughly the size of a small town. You could theoretically walk across its diameter in about an hour if physics allowed such an impossible journey. This reveals something fascinating about black holes. Their mass and their physical size don't relate to each other the way we might expect. They pack enormous amounts of matter into incredibly compact spaces. It's like having the weight of a mountain compressed into a marble. Between these stellar mass black holes and the true giants, there's a mysterious middle category. Intermediate mass black holes weigh hundreds to hundreds of thousands of times more than our Sun. Scientists don't find them very often, and they're not entirely sure how they form. They might grow in dense clusters of stars, where multiple stars collide and merge together over time. These are the quiet middle children of the black hole family, significant but not dominant. Then we reach the supermassive black holes, and the scale jumps dramatically. These monsters weigh millions or billions of times more than our Sun. Every large galaxy seems to have one sitting at its center, including our own Milky Way. Our galactic center hosts something called Sagittarius A star, which contains about 4 million solar masses worth of material. That number is almost impossible to visualize. 4 million stars worth of mass, all concentrated into a region smaller than Mercury's orbit around the Sun. But even 4 million solar masses isn't close to the upper limit. In other galaxies, particularly old and large ones, central black holes can reach hundreds of millions or even several billion solar masses. These are the powerhouses behind quasars, those incredibly bright objects we can see across vast cosmic distances. And then there are the truly extreme cases. Some astronomers use the term ultramassive for black holes that exceed 10 billion solar masses. Take the black hole associated with the quasar TON 618. Current estimates suggest it weighs something like 60 billion times what our Sun weighs. At this point, our normal words completely fail us. Let me try a different approach to convey this scale. Imagine each star, like our Sun, is a grain of sand. A stellar mass black hole would be like a small handful of those grains. The supermassive black hole in our galaxy would fill maybe a coffee cup with sand, but an ultramassive black hole would be more like dumping an entire dump truck full of sand into one spot. Of course, even that comparison falls apart, because we can still picture dump trucks and coffee cups. The reality is that these scales simply don't map onto anything in human experience. We're using familiar words to describe something fundamentally beyond familiar territory. The influence these objects have also scales dramatically with their size. A stellar mass black hole mostly affects its immediate neighborhood. It might pull gas from a nearby companion star, or just sit quietly in space until something drifts too close. Supermassive black holes shape the motion of stars across the central regions of entire galaxies. In our Milky Way, astronomers can track individual stars orbiting near the galactic center. These stars move at incredible speeds, some reaching thousands of kilometers per second as they swing around Sagittarius A star. Ultramassive black holes operate on an even grander scale. They can influence the behavior of entire galaxies and their surroundings. Material falling into these monsters releases so much energy that it heats gas across galactic distances. This affects where and how new stars can form. Sometimes these black holes launch jets of particles that stretch far beyond their host galaxy, reaching into the empty space between galaxies. The difference between big, bigger, and absolutely enormous isn't just about adding more zeros to numbers. It represents different roles these objects play in the cosmic hierarchy. It's about reach, influence, and how they participate in the universe's larger structure. There's also something profound about how these different-sized black holes come to exist. Stellar mass black holes have relatively simple, local stories. They're tied to the life and death of individual stars. Their formation is like a personal cosmic event, affecting mainly their immediate stellar neighborhood. The largest black holes tell much more complex stories. Their growth reflects billions of years of galactic history. They've grown through countless mergers with smaller black holes, by consuming vast amounts of gas and dust, and through processes tied to the formation of large-scale cosmic structures. Their very existence is intertwined with the evolution of their entire galaxy. This raises interesting questions about the nature of size itself. When we say something is larger, we usually mean it takes up more space, or has more mass, or both. But with black holes, size becomes a more nuanced concept. It's about gravitational influence, about the role in cosmic evolution, about the scale of the stories they tell. Perhaps what's most remarkable is that these objects exist at all. The universe somehow allows matter to concentrate to such extreme degrees that space and time themselves become warped beyond recognition. At the event horizon of any black hole, regardless of size, the normal rules of physics as we understand them begin to break down. In contemplating these scales, we're really contemplating the limits of comprehension itself. There's something humbling about reaching the edge of what our language and imagination can handle. We can calculate the numbers, we can make the comparisons, but truly grasping what 60 billion solar masses means might be beyond human cognitive capacity. Yet we keep trying to understand, keep pushing against those limits. Maybe that's what makes us human, this drive to comprehensible, to find meaning in scales that dwarf our entire existence. Black holes present a fascinating puzzle when we think about their size. Mass tells us one story, but the event horizon tells another. The event horizon marks that invisible boundary where space itself gives up, where nothing can turn back. A black hole with the same mass as our Sun creates an event horizon just a few kilometers wide. Imagine something so dense, so compressed, that it warps space into a sphere of darkness smaller than most cities. But scale this up to 1 billion solar masses, and suddenly that boundary stretches out to match Earth's orbit around the Sun, the truly colossal ones. Those with tens of billions of times our Sun's mass push their event horizons out to Neptune's orbit and beyond. Standing at a safe distance, you wouldn't see a point of light disappearing. You'd witness an entire sphere of absolute darkness, large enough to swallow our inner solar system whole. Yet even these immense voids remain tiny compared to their host galaxies. This paradox makes them endlessly intriguing. They dominate everything around them, while occupying almost no space at all. They're the heaviest single objects in their cosmic neighborhoods, yet they take up less room than a fraction of a percent of the total galactic volume. Scientists divide black holes into categories, but these boundaries blur like watercolors in rain. Stellar mass, intermediate, supermassive, ultramassive. These labels help us organize our thoughts, but nature doesn't follow our filing systems. The universe creates what it creates, following physics rather than human convenience. Our knowledge remains incomplete, full of gaps and mysteries. We understand stellar mass black holes fairly well because we can watch them interact with companion stars. We're learning about supermassive ones by studying galactic centers and distant quasars, but intermediate mass black holes hide from us, elusive and hard to confirm. This means our picture of black hole sizes resembles a puzzle with missing pieces. There might be more objects in that middle range than we realize. There could be black holes even larger than our current record holders, lurking in regions of space we haven't examined closely yet. Measuring these cosmic giants requires detective work. Astronomers can't weigh a black hole directly. Instead, they watch how stars dance around invisible partners, how gas behaves near the edge of oblivion, how light gets twisted and stretched by extreme gravity. From these clues, they build models, mathematical frameworks that translate observations into mass estimates. But models carry uncertainty, error bars, ranges of possibility. When we say a black hole weighs 60 billion suns, we really mean it probably falls somewhere within a range around that number. This uncertainty means the title of largest black hole discovered can shift. New measurements might refine old estimates. New discoveries might dethrone current champions. The crown passes from one cosmic giant to another as our understanding deepens. There's something almost human about our fascination with extremes. The universe doesn't care about records. To the cosmos, a black hole with 10 billion solar masses and one with 60 billion are both just outcomes of gravity and time acting over enormous spans. Our labels reflect our need to organize, to find patterns in chaos. From a cosmic perspective, there's no special category for largest. There's just a continuous spectrum of possibilities shaped by local conditions and cosmic history. Yet we can't resist the pull of superlatives. The tallest mountain, the deepest ocean, the brightest star, the most massive black hole. These extremes give us anchor points in an ocean of data. They help us tell stories, frame knowledge in ways that feel meaningful. This tendency appears everywhere in human experience. We mark the biggest moments, celebrate the longest journeys, remember the most important milestones. It's how we create structure, find highlights in what would otherwise be a continuous flow of events. With black holes, breaking records means more than just bragging rights. A truly massive black hole, especially one spotted in the early universe, challenges everything we think we know about cosmic growth rates. How did something accumulate so much mass so quickly after the Big Bang? These discoveries push scientists to rethink galaxy formation, cosmic structure, the behavior of matter under conditions we can barely imagine. The difference between big, bigger, and absolutely enormous becomes a difference in the questions we ask. A small black hole raises questions about stellar evolution, how massive stars end their lives in collapse. A medium one makes us wonder about star clusters, galactic neighborhoods, the complex dance of gravity on intermediate scales. A truly enormous one forces us to examine the history of the universe itself. Time adds another dimension to size that we often overlook. The largest black holes aren't just large in space, they're large in time. They carry within them the accumulated history of billions of years of cosmic activity. Every bit of mass they contain represents something that once existed independently. A star that lived and died, a cloud of gas that never quite became a star, another black hole that got too close and paid the ultimate price. In this sense, an ultramassive black hole resembles a kind of archive. It's a single object that holds the compressed results of countless past events, all squeezed into one gravitational presence. This perspective shifts how we think about size entirely. It's not just about mass or volume, it's about how much history something contains. The largest black holes are like cosmic libraries, their contents written in the language of gravity rather than words. Each one tells a story of growth, influence and time unfolding across distances that quietly remind us just how vast and ancient our universe really is. Imagine standing at the edge of a vast canyon, where the familiar ground suddenly drops away into something that stretches beyond what your eyes can take in. This is what it feels like when we start talking about supermassive black holes. These aren't just bigger versions of regular black holes. There's something entirely different, something that sits in a category all by itself. Most people think of black holes as cosmic vacuum cleaners, wandering around space and sucking up everything in their path. But supermassive black holes, they're more like the ultimate couch potatoes. They just sit there, right at the center of their galaxy, barely moving at all. Everything else, the stars, the gas clouds, the entire spiral arms of the galaxy, they're all dancing around this massive, invisible partner. Our own galaxy has one of these giants. Scientists call it Sagittarius A star, and it weighs about 4 million times as much as our Sun. 4 million. Just try to wrap your mind around that number for a second. And here's the thing, that's actually considered small in the world of supermassive black holes. Some of the really big ones out there, they can weigh billions of times more than the Sun. When we say supermassive, we're talking about mass that starts at around 1 million suns and just keeps going up from there. Regular black holes, the ones that form when stars collapse, they might weigh anywhere from a few suns to maybe a few dozen. There's this enormous gap between the two types, like comparing a pebble to a mountain. But here's something that might surprise you. The bigger these black holes get, the less dense they become on average. It sounds backwards, doesn't it? Yeah, that sounds backwards, doesn't it? We think of black holes as the ultimate compression, matter squeezed down to impossible densities. And that's still true at their core. But when you look at the whole picture, when you consider that the boundary of a supermassive black hole can be as wide as a planet's orbit, all that mass is spread out over a much larger space. If you could somehow find yourself drifting toward the edge of one of these giants, you might not even notice when you cross the point of no return. The forces at that boundary can be surprisingly gentle, much more so than around smaller black holes where the pull can literally stretch you apart. It's almost poetic in a way. These cosmic titans are gentle at their edges, even though their grip is absolutely final. Nearly every large galaxy we've ever studied has one of these supermassive black holes sitting right at its heart. Spiral galaxies like ours, those big elliptical galaxies that look like glowing clouds of stars. Even some of the smaller galaxies, they all seem to have one. This tells us something profound, that these objects aren't just rare accidents of physics. They're a fundamental part of how galaxies work, how they form and grow and change over time. Scientists have been trying to figure out which came first, the galaxy or the black hole at its center. It's a bit like asking whether the chicken or the egg came first. The evidence suggests they grew up together, influencing each other over billions of years of cosmic history. In our own galaxy, astronomers have been watching individual stars as they orbit around our central black hole. These stars move incredibly fast, tracing long, stretched-out paths that reveal the presence of something massive and invisible at the center. By measuring how fast these stars move and how close they get, scientists can calculate exactly how much our black hole weighs. It's like watching a cosmic dance, where the steps tell you everything about the invisible partner. For galaxies that are too far away to see individual stars, astronomers use different tricks. They analyze the light coming from the hot gas swirling around the black hole, looking at how fast it's moving and how much space it takes up. From this, they can figure out the mass of the black hole hiding in the center. This research has revealed something fascinating. The mass of the black hole at the center of a galaxy is often related to the mass of the galaxy's central bulge of stars. It's as if they've been growing together, keeping pace with each other over cosmic time. The black hole influences the galaxy, and the galaxy influences the black hole, in a kind of cosmic conversation that's been going on for billions of years. When a supermassive black hole starts feeding, when there's plenty of gas and dust falling into it, amazing things happen. The material forms a bright, hot disk as it spirals inward. Sometimes, powerful jets of particles get launched from near the black hole's poles, shooting out at nearly the speed of light. These jets can stretch far beyond the galaxy itself, carrying enormous amounts of energy into the space between galaxies. This energy can have a huge impact on the galaxy. It can heat up gas clouds, preventing them from cooling down and forming new stars. It can even push gas completely out of the galaxy. In this way, a supermassive black hole can control how many new stars its galaxy can make. When the black hole is very active, it can essentially shut down star formation. When it's quiet, the galaxy can get back to making new stars. It's a delicate balance, this relationship between a galaxy and its central black hole. The black hole isn't just sitting there passively, it's an active participant in the life of the galaxy, helping to shape its evolution over cosmic time. In a way, it's the galaxy's regulator, determining when it's time to grow and when it's time to rest. This raises profound questions about our place in the universe. Our sun, our solar system, our entire local neighborhood of stars, we're all part of this vast system that's been shaped by the presence of a 4 million solar mass black hole sitting quietly at the center of our galaxy. Every star in the night sky is following a path that's been influenced in some small way by this invisible giant. The study of these supermassive black holes is still a young field. We're constantly discovering new things about how they work, how they form, how they influence their surroundings. Each new observation adds another piece to the puzzle, helping us understand not just these individual objects, but the larger story of how the universe has evolved over the past 13 billion years. The formation of supermassive black holes remains one of astronomy's most puzzling questions. Scientists have proposed several pathways, each offering a different window into the early universe's mysterious workings. The first generation of stars, those primordial giants, likely left behind black holes much larger than anything we see forming today. These ancient remnants would have enjoyed a significant head start, already weighing dozens of times more than our sun. Through millions of years of feeding and merging, they could eventually reach the supermassive realm. But there's another possibility, one that bypasses stars entirely. In the universe's infancy, under very specific conditions, enormous gas clouds might have collapsed directly into black holes. No stellar phase, no nuclear burning, just a straight plunge into gravitational darkness. These direct collapse events could birth black holes weighing thousands, even millions of solar masses right from the start. Then stellar nurseries offer yet another pathway. Imagine crowded regions where stars and smaller black holes constantly bump into each other, merging repeatedly over cosmic time. Each collision builds something bigger, like stones gathering into an avalanche. The truth probably involves all these mechanisms working together, each dominating in different cosmic neighborhoods. What makes this puzzle particularly intriguing is the discovery of massive black holes in the very early universe. When we peer at quasars billions of light years away, we're seeing them as they were when the cosmos was just a cosmic toddler. These observations present a timing problem. If black holes grow at the rates our models predict, some of these ancient giants shouldn't exist yet. They're like finding a fully grown oak tree in a forest that was planted yesterday. Something doesn't quite add up, and that's where science gets interesting. These contradictions force us to reconsider our assumptions. Perhaps black holes can grow faster than we thought. Maybe the early universe offered feeding conditions we haven't fully understood. Or possibly, our theories need fundamental adjustments. There's something uniquely challenging about studying supermassive black holes. You never actually see the object itself. Instead, you observe its gravitational fingerprints scattered across space. Stars whip around invisible anchor points at tremendous speeds. Gas spirals inward, heating up until it glows brighter than entire galaxies. Massive jets shoot outward, stretching across millions of light years. The black hole remains hidden throughout this cosmic theater, like a director working behind the scenes. Its presence shapes every performance, yet it never takes the stage. This indirect detection method teaches us something profound about influence and visibility. The most powerful forces often work unseen. Consider the strange mathematics of galactic architecture. A supermassive black hole might outweigh hundreds of millions of stars, yet those stars provide virtually all the light we observe. The black hole dominates gravitationally, but remains optically invisible. This creates a fascinating tension between mass and luminosity, between what matters most and what we actually see. This pattern repeats throughout modern astronomy. Dark matter outweighs visible matter by enormous margins. Dark energy drives cosmic expansion, while remaining completely mysterious. The universe seems built on invisible foundations, with the bright, familiar objects serving as mere decoration on a hidden framework. The mythological term, Titan, carries appropriate weight here. Ancient Titans weren't the heroes of everyday stories. They were the foundational powers, the deep structural elements that defined reality's basic rules. Supermassive black holes play a similar role in cosmic mythology. These objects formed early, when the universe was young and wild. They've witnessed billions of years of stellar birth and death, galactic collisions, and the universe's gradual expansion. Most of the time, they sit quietly at galactic centers, patient and watchful. But their gravitational influence shapes everything around them across vast timescales. There's a meditative quality to contemplating these cosmic anchors. They embody patience on an almost incomprehensible scale. While stars blaze and die in mere millions or billions of years, supermassive black holes persist almost indefinitely. They're the universe's most permanent residents, slowly accumulating mass and growing ever more influential. The accretion process itself reveals nature's efficiency. Gas doesn't simply fall straight down into a black hole. Instead, it forms elegant spirals, conserving angular momentum, while gradually losing energy. These accretion disks become some of the hottest, brightest objects in the universe, converting gravitational potential energy into electromagnetic radiation with stunning efficiency. When supermassive black holes do become active, feeding heavily and launching jets, they can outshine their entire host galaxies. Yet this represents only a tiny fraction of the infalling matter's mass, converted to energy through processes more efficient than nuclear fusion. The rest disappears forever behind the event horizon. Adding to the black hole's gravitational influence, these feeding frenzies don't last forever. Eventually, the nearby gas supply diminishes, and the black hole returns to relative quiescence. But even quiet, supermassive black holes continue shaping their neighborhoods through pure gravitational presence. They're like sleeping giants, temporarily dormant but never truly inactive. The relationship between supermassive black holes and their host galaxies reveals cosmic symbiosis. Larger galaxies typically harbor more massive central black holes, suggesting these objects grow together over cosmic time. Neither completely dominates the other. Instead, they engage in a delicate gravitational dance, each influencing the other's development. This cosmic partnership raises profound questions about causation and correlation. Do big galaxies create big black holes, or do big black holes enable big galaxies to form? The answer probably involves mutual feedback, with each component responding to and shaping the other across billions of years. Understanding supermassive black holes ultimately means grappling with invisible architecture. The universe's most important structural elements remain hidden from direct observation, knowable only through their effects on visible matter. It's a humbling reminder that reality extends far beyond the reach of our senses, operating according to principles we're still learning to perceive. Light carries stories across the cosmos, traveling for billions of years through expanding space before reaching our telescopes. These ancient photons bring news from distant realms, carrying information about objects so massive they reshape our understanding of what's possible in the universe. When we look deep into space, we're actually looking back in time. The light from the most distant object started its journey when the universe was young, when our solar system didn't even exist yet. This creates a fascinating window into cosmic history, where astronomy becomes a kind of time travel. Among the faintest points of light in our telescopes lies something extraordinary. An object called TOT 618 appears as just another star-like dot, but appearances can be deceiving. What we're actually seeing is a quasar, one of the most energetic phenomena in the universe. Quasars form when supermassive black holes actively feed on surrounding material. Gas and dust spiral inward, creating a flat, swirling disk around the black hole. Friction and compression heat this material to incredible temperatures, causing it to glow brilliantly across the entire electromagnetic spectrum. Sometimes, jets of particles shoot out from near the black hole's poles at nearly the speed of light. This cosmic feast creates a beacon so bright it can outshine entire galaxies. From our perspective, billions of light years away, all this activity appears as a single, intensely bright point. It's like watching a distant lighthouse, where the complexity of the mechanism is hidden behind the simple appearance of the light itself. The black hole, powering TON 618, weighs approximately 60 billion times more than our Sun. This number pushes against the comfortable boundaries of what we thought possible. Most black holes, even the supermassive ones at galaxy centers, weigh millions or perhaps tens of billions of solar masses, but 60 billion represents something different. Something that challenges our models of how these objects form and grow. To grasp this scale, consider our Sun's gravitational influence. It holds the entire solar system together, controlling the orbits of planets across billions of kilometers. Now, multiply that gravitational presence by 60 billion. The result is a region of space where physics operates under the most extreme conditions imaginable. If this black hole replaced our Sun, its event horizon would extend far beyond Neptune's orbit. The event horizon marks the boundary where escape becomes impossible, where space and time themselves become so warped that nothing, not even light, can return. Everything we call the solar system would fit comfortably within this forbidden zone. Yet this massive object still represents just a tiny fraction of its host galaxy. This creates an interesting paradox, where something enormously dominant on one scale becomes relatively insignificant on another. It's a reminder that the universe operates on multiple levels simultaneously, with different rules governing different scales of existence. The distance to TON 618, more than 10 billion light-years, adds another dimension to its significance. When we observe this object, we're seeing it as it existed when the universe was much younger. Earth hadn't formed yet, the Sun was still just scattered dust and gas, and our galaxy was still assembling itself from smaller pieces. This temporal displacement raises profound questions about cosmic evolution. How did such a massive black hole exist so early in universal history? What conditions allowed it to accumulate mass so quickly? The answers challenge our understanding of how structures form and grow in the cosmos. Measuring the mass of something so distant requires clever techniques. For nearby black holes, astronomers can watch individual stars orbiting the central mass, calculating the invisible object's weight from the stellar motion. But at TON 618's distance, individual stars blur together into an indistinct glow. Instead, scientists analyze the quasar's light itself. The hot gas spiraling around the black hole produces characteristic features in its spectrum. These emission lines broaden when the gas moves quickly, stretched by the Doppler effect. By measuring how wide these lines appear and how bright the overall quasar shines, astronomers can estimate the size of the emitting region and the speed of the orbiting material. From these observations, they calculate the gravitational strength needed to accelerate gas to such velocities. It's like determining the size of a whirlpool by studying the motion of debris caught in its currents. The faster the material moves, the stronger the central pull must be. This indirect approach carries uncertainties, but multiple independent measurements point toward the same remarkable conclusion. The numbers consistently suggest a black hole of unprecedented mass, sitting at the very edge of what theoretical models predict as possible. The existence of TON 618 forces us to reconsider fundamental questions about cosmic architecture. Black holes don't just grow by swallowing nearby material, they also merge with other black holes when galaxies collide. But even accounting for these processes, 60 billion solar masses represents an almost incomprehensible accumulation of matter and energy. Perhaps most intriguingly, TON 618 may not be unique. As our telescopes become more sensitive and our surveys more comprehensive, we might discover that such extreme objects are less rare than we currently imagine. Each new discovery reshapes our perspective on what the universe contains and how it evolved. The philosophical implications extend beyond astronomy. Here we have an object so massive that it warps space-time itself, creating a region where our normal understanding of physics breaks down completely. Yet this extreme environment exists as part of the same universe that produced planets, stars, and eventually, conscious beings capable of contemplating their own cosmic context. In studying TON 618, we encounter the strange relationship between the observable and the invisible, between what we can measure and what remains forever hidden behind the event horizon. The black hole reveals itself only through its effects on surrounding matter, like a cosmic shadow defined by the light it bends and captures. This dance between matter and energy, between the visible and invisible, between the ancient past and our present observations, captures something essential about the nature of scientific discovery. We piece together cosmic truths from fragments of light, building models of reality from the faintest signals reaching across impossible distances. Black holes don't reveal their masses easily. Like stepping on a bathroom scale, scientists have to work with models, educated guesses, and ranges of possibilities instead. Even with all these uncertainties, research teams using completely different methods keep coming back to the same shocking numbers for this particular object. The raw mass itself is staggering, but what really catches your attention is how far it sits from everything else we know about. Most supermassive black holes tip the scales at millions or billions of solar masses. This one sits in a realm so extreme that researchers had to invent a new category. They call objects like this ultramassive black holes, a way of saying they've moved beyond the normal definition entirely. It's like finding an animal so large that the word giant doesn't fit anymore. When you stop to think about what it takes for something like this to exist, the early universe starts to make more sense as a breeding ground for monsters. Matter was packed together more tightly back then. Galaxies bumped into each other regularly. Gas clouds were everywhere, ready to be consumed. All of these conditions could feed a growing black hole at incredible rates. But even in that rich environment, building something this massive isn't straightforward. Black holes face a fundamental limit to how fast they can grow. Gravity pulls matter inward, but the intense radiation from all that falling material pushes back just as hard. It's a cosmic tug-of-war that sets a speed limit on growth. This means our ultramassive giant either started from something already enormous, or it found itself in the perfect storm of conditions, or both. One possibility is that it formed where multiple galaxies crashed together early on, funneling gas and smaller black holes into one central feeding frenzy. Another idea suggests it might have formed through direct collapse, where a massive gas cloud just gave up and became a black hole all at once, skipping the usual step of forming from a single dying star. These formation stories are still being worked out, and objects like this serve as natural laboratories for testing ideas. If scientists can figure out how this particular monster grew so large, they can apply that knowledge to other cosmic heavyweights and build a clearer picture of how black holes form in general. There's a bigger implication hiding here, one that reaches far beyond black holes themselves. If objects this massive were common in the early universe, they would have completely reshaped how galaxies formed around them. The energy pouring out of their accretion disks and jets would have heated up surrounding gas clouds, deciding where and when new stars could be born. This means the largest black holes weren't just sitting passively in space, collecting matter. They were active participants in cosmic architecture, influencing the large-scale structure of everything around them. When you think about something changing everything, it's not just about changing scientific theories. It's about how such an object might have rewritten the rules for its entire cosmic neighborhood. The discovery itself didn't happen in a single dramatic moment of revelation. It emerged gradually through sky surveys, quasar catalogues, and patient follow-up observations. As astronomers measured its properties and compared them to others, its exceptional nature slowly became clear. This reflects how most big discoveries actually work in science. Instead of dramatic eureka moments, you get the accumulation of many small, careful steps. Data gets collected, analyzed, questioned, and refined. Patterns emerge slowly, like a photograph developing. There's something fitting about this when it comes to black holes. Objects defined by patience, gravity, and vast timescales get revealed through equally patient and methodical work. It's worth remembering that this object holds its title only for now. Science doesn't deal in permanent records. It deals in current best estimates. There might be black holes out there that are just as massive, or even more so, hidden in regions of space we haven't studied in detail yet. As telescopes become more powerful and surveys become more comprehensive, new candidates will probably emerge. This doesn't diminish what we've found. Instead, it places the discovery within an ongoing story, one where each finding opens the door to the next. The universe has a way of surprising us, just when we think we found the most extreme example of something. Take a moment to consider what it means on a human level to discuss something like this. We're talking about an object billions of light years away, outweighing billions of stars, existing on timescales that make all of human history look like a brief flicker. And yet, here we are, on a planet orbiting a fairly ordinary star, able to detect its presence and estimate its mass. This connection across such vast distances and times represents one of the quiet marvels of science. The same physical laws that govern how your coffee cools in the morning also govern the behavior of superheated gas spiraling around a black hole at the edge of the observable universe. When you think about it this way, distant cosmic monsters aren't just abstract objects. They're part of the same system of reality that includes you, your surroundings, and every small, everyday event. There's also a subtle shift in perspective that can come from contemplating something so extreme. It can make everyday worries feel lighter, if only temporarily. It reminds you that the universe is wide, deep, and full of things that exist far beyond the immediate scope of daily life. This doesn't mean the details of everyday life are unimportant. It simply means there's room sometimes to let your mind wander outward and take in a larger view. This particular object serves as both a specific thing and a symbol. It's specific in the sense that it has a location, a mass, a spectrum of light, and a measurable history. It's a real physical thing that can be studied and compared to others. It's also symbolic because it represents the extreme end of a process that happens throughout the universe. Black holes grow everywhere, in many galaxies, under many different conditions. This one simply happens to sit at the far end of that range, making it a useful marker for what's possible. It's like finding the tallest mountain or the deepest ocean trench, a natural benchmark for the universe's capacity to build extreme things. There are other contenders for the title of largest black hole. Some sit in the centers of massive galaxies in our cosmic neighborhood. Others power distant quasars, similar to this one. Each has its own story, its own environment, and its own path of growth. Comparing them helps scientists identify common patterns and important differences. This is where focusing on the largest known black hole becomes more than just studying a single object. It becomes a way of exploring a whole class of extreme phenomena. These cosmic giants mark not just physical boundaries, but boundaries of knowledge itself. They stand as reminders that the universe is capable of building things far beyond what we can easily imagine. Our role as observers and thinkers is to keep tracing the outlines of those things, slowly and carefully, as far as our tools and curiosity will allow. Across the vast stretches of space, these monsters wait patiently, challenging everything we thought we knew about how big things can get. The universe overflows with light in countless forms. Stars burn with steady brightness. Galaxies spread their collective glow across vast stretches of sky. Gas clouds illuminate when energy from nearby sources excites them. But in the midst of all this radiance, black holes exist as profound absences. They define themselves not by what they reveal, but by what they consume. These cosmic voids challenge our understanding of observation itself. How do you measure something that exists by negating light? How do you weigh an absence? The answer lies in learning to read the universe like a detective story, where the most important character never appears on stage. Think of space as a theater where invisible actors shape every scene. Even when the main player remains hidden, the movements of everyone else reveal exactly where they stand. Black holes announce themselves through influence rather than appearance, through the dance they force upon their cosmic neighbors. Movement provides the most straightforward clue. In daily life, you sense heavy objects without seeing them. A ball rolling across a floor suddenly curves, suggesting a slope or gravitational pull nearby. Space operates on similar principles, just with stars and gas clouds playing the role of rolling balls. These celestial objects follow paths carved by gravity. By watching their trajectories carefully, astronomers decode what forces guide them. Near the center of our own galaxy, scientists have spent decades tracking individual stars as they race around an invisible point. Some complete their loops in mere years, traveling thousands of miles per second. Only an object with tremendous mass packed into a tiny space could hold these stars in such violent orbits without losing them to the void. By mapping these paths, measuring speeds, and applying gravitational laws, researchers calculate exactly how massive that central darkness must be. This method revealed the weight of our galaxy's central black hole with remarkable precision. Distance, however, limits this approach. For black holes in remote galaxies, individual stars blur into a single glow. The galactic center becomes a bright point rather than a collection of distinct objects, so astronomers turn to light itself as a messenger. Black holes may not emit light, but the material spiraling toward them certainly does. Gas falling into these cosmic drains forms spinning disks that heat up dramatically. These accretion disks glow across numerous wavelengths, carrying information about temperature, motion, and composition. Spectroscopy unlocks this information by spreading light into its component colors, like a prism creating rainbows from white light. Within these rainbows, dark and bright lines appear at specific wavelengths, revealing which elements are present and under what conditions the light was born. Motion adds another layer to this story. Light from approaching sources shifts slightly toward blue wavelengths. Light from retreating sources shifts toward red. This Doppler effect works for light, just as it does for sound, explaining why a passing siren changes pitch as it moves past you. In the swirling disk around a black hole, gas moves at incredible speeds in all directions. Some approaches us, some recedes, some travels sideways. This motion causes spectral lines to broaden and spread out. The faster the gas moves, the wider these lines become. By measuring line width, astronomers estimate gas velocity. From velocity, they infer gravitational strength needed to maintain those orbits. Stronger gravity indicates more massive black holes. This technique proves especially valuable for studying quasars, where accretion disks shine brightly across billions of light years. Brightness itself offers additional information. The intensity of a quasar helps estimate the size of its light-producing region. Brighter objects generally involve larger or more energetic emission zones. Combining size estimates with speed measurements allows astronomers to calculate central black hole masses. These calculations require sophisticated models of accretion disk behavior. Scientists test their models against observations of nearby, better understood systems. Over time, models improve and estimates become more reliable. Space itself bends around massive objects, according to general relativity. This curvature forces light to follow curved paths near heavy concentrations of matter. The effect, called gravitational lensing, can distort, magnify, or multiply the appearance of background objects. Sometimes a black hole, or its host galaxy, acts as a lens for light from even more distant sources. By studying how background illumination bends, astronomers learn about the mass responsible for the distortion. While not the primary method for measuring black hole masses, lensing adds valuable context to the overall picture. Timing provides yet another approach. In systems with smaller black holes and companion stars, astronomers observe regular brightness changes as objects orbit each other. Measuring the period of these variations reveals orbital sizes and masses involved. For supermassive black holes, a related concept called reverberation mapping comes into play. This technique examines how brightness changes in the accretion disk echo through surrounding gas clouds. When the disk brightens, light takes time to reach these clouds and make them glow. By measuring this delay, astronomers estimate distances between disks and clouds. Combined with gas speed measurements, this leads to another mass estimate for the central black hole. All these methods share a fundamental approach. They avoid looking at black holes directly. Instead, they examine how these objects influence their neighborhoods. This makes black hole measurement a form of cosmic archaeology, where scientists reconstruct invisible giants from the traces they leave behind. The precision achieved through these indirect methods seems almost miraculous. We can weigh objects we cannot see, measure sizes we cannot observe, and map influences we can only infer. This speaks to something profound about the nature of knowledge itself. Sometimes understanding comes not from direct observation, but from learning to read the subtle language of cause and effect. Black holes present us with one of the universe's greatest paradoxes. These objects are defined by their invisibility, yet we've managed to weigh them with surprising precision. The process resembles detective work on a cosmic scale, where scientists piece together evidence from the faintest of clues. When we look at distant quasars, we're essentially time travelers, examining light that began its journey billions of years ago. This ancient light carries within it the story of its origin, encoded in wavelengths and patterns that tell us about the monster lurking at the galaxy's heart. But this light doesn't arrive pristine. It's been weathered by its long journey through space, scattered by gas clouds, stretched by the expansion of the universe itself. The light that finally reaches our telescopes is just a whisper of its former self. Every photon has been altered, distorted, and filtered through countless cosmic encounters. Scientists must work backwards from this corrupted signal, like archaeologists reconstructing a civilization from fragments of pottery. They strip away the noise correct for instrumental quirks and slowly reveal the original message hidden within. What emerges from this painstaking process is remarkable. The signature of matter swirling around an invisible drain. Gas clouds heated to millions of degrees emit specific wavelengths as they spiral inward toward their doom. The speed of this cosmic dance, the Doppler shifts in the light, the timing of flares and echoes, all these details whisper secrets about the mass of the central object pulling the strings. There's something almost philosophical about measuring something by its absence. We're quantifying darkness itself, using the very light it consumes as our ruler. The gas orbiting a black hole moves faster when the gravitational pull is stronger, and stronger pull means more mass. It's like judging the size of a whirlpool by watching leaves circle its edge. Different teams around the world tackle these measurements using various approaches. Some focus on the broad iron lines in X-ray spectra, others track the motion of individual stars, still others time the echoes of light bouncing off the accretion disk. When these independent methods agree, confidence builds, like witnesses corroborating the same story from different vantage points. The human element in this process often goes unnoticed. Behind every measurement lies years of collaborative effort, teams of researchers designing instruments, writing software, debating interpretations. Data gets checked and double-checked, results compared with previous studies, papers scrutinized by peer reviewers. This careful, methodical approach gives weight to the final numbers. They're not just calculations, but the product of collective scientific endeavor. Recently, a completely new method has emerged, one that doesn't rely on light at all. Gravitational waves offer us a direct line to black hole behavior, ripples in spacetime itself, caused by the most violent events in the universe. When two black holes spiral into each other, they send shock waves through the fabric of reality, waves so subtle they can barely nudge a laser beam by less than the width of a proton. Yet from these whisper-quiet signals, scientists can determine not just the masses of the merging black holes, but their spins, their orbital dynamics, even details about their final moments. It's like listening to the universe's heartbeat, feeling its pulse through instruments of extraordinary sensitivity. This gravitational wave astronomy works best for smaller black holes so far. The mergers of supermassive black holes produce waves with frequencies too low for our current Earth-based detectors to catch easily, but future space-based instruments may open this window wider, letting us eavesdrop on the growth and interaction of the largest black holes across cosmic time. There's something profound about using space-time itself as a sensor. We've moved beyond just collecting light to feeling the universe's vibrations, like placing our ear to the ground to hear distant footsteps. The fabric of reality becomes our instrument, responding to the most extreme gravitational events with patterns we can decode and interpret. This whole approach reflects a deeper principle in science. When something can't be observed directly, you look for its influence on everything else. It's a strategy that appears throughout scientific investigation, from studying Earth's interior through seismic waves to understanding subatomic particles through their decay signatures. The common thread is learning about the hidden through its effects on the visible. There's quiet elegance in this indirect approach. It suggests that nothing exists in complete isolation. Even the most secretive objects in the universe leave their mark somehow. Black holes may swallow light, but they can't hide their gravitational influence, their effect on nearby matter, their distortion of space and time itself. The measurement of black hole masses becomes a testament to human ingenuity, our ability to reason from effect back to cause. We've developed chains of logic that connect what we can detect to what we want to understand, building bridges across the vast gulf between the observable and the hidden. In some ways, this mirrors how we approach many mysteries in life. Understanding often comes not from staring harder at what puzzles us, but from widening our view, examining the context, looking for patterns in the surrounding details. The black hole story is written not in its darkness, but in everything around it, in the motion of stars, the heating of gas, the bending of light rays. Even the most isolated objects participate in the cosmic conversation. They influence their neighbors, leave traces of their presence, create ripples that propagate across space and time. The universe maintains no perfect secrets. Every massive object announces itself through gravity. Every hot gas cloud glows with characteristic light. Every violent event sends signals racing outward at light speed. The largest black holes in the universe may be invisible, but they're far from silent. They orchestrate vast symphonies of matter and energy, conducting cosmic dances that we can observe and decode from billions of light years away. In measuring these distant monsters, we're really measuring our own capacity for understanding, our ability to find meaning in signals so faint they barely register above the background noise of space. Picture the cosmos constructing cities that dwarf anything we could ever imagine. These cities stretch across distances so vast that light itself takes tens of thousands of years to cross from one edge to another. Each city contains hundreds of billions of residents, all of them stars, arranged in beautiful spiraling neighborhoods and glowing districts. Yet, at the very heart of these cosmic metropolises, there often sits something that seems to contradict the entire arrangement. Complete darkness, a region where nothing, not even light, can escape once it ventures too close. This darkness doesn't announce itself with fanfare or bright signs. It simply exists, invisible, yet undeniably present, shaping everything around it through the most fundamental force in the universe, gravity. The invisible hand that reaches out and touches every star, every wisp of gas, every grain of cosmic dust within its domain. It's a strange thought, really, that something we cannot see directly could serve as the foundation around which entire galaxies organize themselves. When we look at photographs of galaxies, we're seeing them flattened, like pressed flowers in a book. But these structures exist in 3 dimensions, with thickness and depth that extend far beyond what our eyes can easily grasp. Stars don't live in a single, flat plane. They occupy a thick disk, surrounded by a central bulge that swells outward like a cosmic loaf of bread. Beyond that lies an even more mysterious region, a halo of ancient stars and invisible matter that extends into the darkness of space. Gas drifts through all of these regions, sometimes gathering in brilliant nurseries where new stars are born, sometimes flowing in quiet streams that snake between the older stellar populations. All of this material, every atom and particle, feels the pull of gravity from every other piece of matter in the system. It's a cosmic symphony where billions of individual notes combine to create something greater than the sum of its parts. Most large galaxies harbor these massive black holes at their centers, objects so dense that they warp space and time around themselves, creating gravitational wells from which nothing can escape once it crosses a certain boundary. Yet here's the fascinating part. These black holes aren't the primary architects of their galaxies. The combined mass of all those stars, plus vast amounts of invisible dark matter, plays a much larger role in shaping the overall galactic structure. The black hole's direct influence is strongest in the central regions, where stars race around at speeds that would make our fastest spacecraft look like they're standing still. Gas swirls in tight, frenzied orbits, heating up until it glows with the energy of 1 trillion suns. But even though the black hole isn't the main gravitational player in the galaxy, its presence seems to be deeply connected to the galaxy's properties in ways that astronomers are still trying to fully understand. There's a remarkable relationship that emerges when you study many different galaxies. The more massive the central bulge of stars, the more massive the black hole tends to be. This isn't just a loose correlation, it's a tight, predictable relationship that holds across galaxies of many different sizes and types. It's as if the black hole and the galaxy grow up together, each one influencing the other's development over billions of years. Think about how material moves through these cosmic cities. Galaxies aren't frozen structures. They're dynamic, living systems where gas flows and churns, driven by gravity and by the immense energies released when massive stars explode at the end of their lives. This gas can cool and collapse to form new generations of stars. But it can also drift inward, eventually reaching the central regions where the black hole waits. When enough material accumulates around a black hole, something remarkable happens. The black hole begins to feed, and as it does, the surrounding gas forms a swirling disk that can outshine the combined light of all the stars in the galaxy. The black hole itself remains invisible, but the material spiraling into it becomes one of the brightest phenomena in the universe. We call these feeding black holes by various names: quasars, active galactic nuclei, blazars. But they're all fundamentally the same thing: a massive black hole in the process of consuming the matter around it. The energy released during these feeding frenzies doesn't stay politely confined to the black hole's immediate neighborhood. It radiates outward as intense beams of light and high-energy particles. Sometimes it erupts in jets that shoot out from the black hole's poles at nearly the speed of light. These outflows can travel for hundreds of thousands of light years, carrying enough energy to heat and push around the gas throughout the entire galaxy. This is where the black hole's influence becomes truly galactic in scope. When those energetic outflows slam into clouds of gas that would otherwise cool and form new stars, they can heat that gas to temperatures of millions of degrees. Hot gas doesn't collapse to form stars. It expands and flows away. In this manner, an active black hole can regulate, or even shut down, star formation across vast regions of its host galaxy. It's a delicate dance that plays out over hundreds of millions of years. The galaxy provides the black hole with fuel to grow. In return, the black hole releases energy that affects how the galaxy can use its remaining gas reserves. Sometimes this relationship is quiet and stable. The black hole sits dormant while stars form steadily throughout the galaxy. Other times, the black hole becomes active and its influence becomes much more dramatic. Consider the inner structure of these cosmic cities in more detail. At the very center lies the core, where stars are packed together far more densely than in our own solar neighborhood. Here, the black hole's gravity dominates, and stars follow complex, often highly elongated paths. Some of these stars venture remarkably close to the black hole before swinging back out in wide arcs. By tracking the motions of these stars, astronomers can actually measure the mass of the invisible black hole with remarkable precision. Surrounding this core region, many galaxies have a bulge of older stars. These stellar populations tend to be ancient, having formed billions of years ago when the galaxy was young. The stars appear red in color, because they've used up much of their nuclear fuel and have cooled over their long lifetimes. This bulge region is more spherical and less organized than the outer parts of the galaxy. Beyond the bulge, spiral galaxies display their most photogenic feature. The disk, with its graceful spiral arms traced out by young, bright blue stars and glowing clouds of gas. This is where most of the galaxy's current star formation takes place. The spiral pattern itself is a kind of cosmic traffic jam, where gas and stars bunch up as they orbit the galactic center, temporarily creating these beautiful curved structures. Even farther out lies the galactic halo, a roughly spherical region that extends well beyond the visible edges of the galaxy. This halo contains some of the galaxy's oldest stars, but more importantly, it's filled with dark matter, an invisible form of matter that outweighs all the visible stars and gas combined. The dark matter in the halo provides much of the gravitational scaffolding that holds the entire galaxy together. The black hole sits at the center of this entire structure, embedded within the dense stellar core. While its gravitational influence is strongest there, the feedback processes it can trigger have the potential to affect the galaxy on much larger scales. Through the energy it releases during active periods, it becomes a major player in the galaxy's evolution, even though it represents only a tiny fraction of the galaxy's total mass. When black holes grow to truly enormous sizes, their influence becomes even more dramatic. The largest known black holes are so massive that when they become active, they can release enough energy to create giant cavities in the surrounding gas. These cavities can be hundreds of thousands of light years across, large enough to contain multiple smaller galaxies. They appear as vast bubbles of hot, thin gas that have been inflated by the black hole's energetic outflows. These enormous structures tell us that, in the most extreme cases, a black hole's influence isn't confined to its host galaxy. It can reshape the entire local environment, affecting the behavior of gas and galaxies across massive regions of space. It's a reminder that even though black holes are points of darkness, their effects can light up and heat vast volumes of the universe. There's also a connection between the size of these central black holes and the types of galaxies they inhabit. The most massive black holes typically reside in the most massive galaxies, giant elliptical galaxies that often sit at the centers of entire clusters of galaxies. These galactic giants are usually ancient systems where most star formation ended long ago. Their stellar populations are old and red, and their structure is smooth and rounded, rather than organized into spiral patterns. It makes you wonder about the deep connections that exist throughout the cosmos. How something as small as a black hole, relative to the galaxy around it, can play such an important role in shaping these vast stellar communities. How darkness and light, destruction and creation seem to work together in ways that create the beautiful, complex structures we observe scattered throughout space. Perhaps there's something profound in this arrangement. The idea that even the most destructive forces in nature can serve constructive purposes when viewed from the right perspective and over the right timescales. That what appears dark and empty from one viewpoint can be the organizing principle around which entire worlds of stars arrange themselves. Large galaxies often develop through countless collisions with their smaller neighbors. Each time two galaxies merge, something remarkable happens. Stars get redistributed, gas clouds combine, and if both galaxies have central black holes, those merge too. This cosmic dance of destruction and creation has been going on for billions of years, building the massive structures we see today. The biggest black holes, the real monsters of the universe, tend to live in the hearts of galaxies that have experienced many of these mergers. It's like they've been collecting mass through cosmic history, growing larger with each galactic meal. Meanwhile, smaller galaxies that have lived quieter lives, away from all the cosmic traffic, usually host much smaller black holes. Their growth stories are gentler, shaped more by steady processes than dramatic collisions. There's something profound about this pattern. The most extreme objects in our universe, these supermassive black holes, are products of the busiest, most chaotic neighborhoods. Violence and collision, on cosmic scales, create the conditions for the most extraordinary growth. Now picture this for a moment. Imagine you could somehow find yourself living on a planet near the center of one of these massive galaxies. The night sky above you would be nothing like what we see from Earth. Stars would be packed so densely that darkness would be rare. Millions upon millions of suns would create a continuous glow across the heavens. The sheer brightness might make traditional night almost impossible, and at the very center of all this stellar brilliance, there might be something even brighter. If the central black hole happens to be feeding actively, it could create a beacon of energy that outshines entire regions of stars. The radiation pouring out from this feeding process would fill the surrounding space, potentially affecting how new stars form, maybe even influencing the climate and conditions on planets throughout that central region. But black holes don't stay active forever. They have quiet periods too. During these calmer times, the galaxy might look much more peaceful. Star formation would continue in the outer regions, while the inner areas would be dominated by older, more mature stars. This back and forth between active and quiet phases happens over millions or billions of years. The relationship between a galaxy and its central black hole changes constantly. They're locked in this long, slow dance together, each influencing the other across vast stretches of time. Neither stays the same. Both evolve, both grow, both change the conditions around them. Here's something that might keep you thinking. As our universe continues to expand, galaxies are moving farther and farther apart from each other. This means those dramatic mergers that help build the largest black holes are becoming less common. Gas that could feed these cosmic monsters is getting more spread out, harder to collect. The opportunities for rapid growth are slowly disappearing. Far in the future, many galaxies will have used up most of their available gas. Their central black holes will go hungry, fed only by the occasional unlucky star that wanders too close, or a stray cloud of dust. The active, energetic relationship between galaxy and black hole will fade into something much quieter, much more stable. This long-term perspective reveals something beautiful about cosmic evolution. We're not just talking about objects arranged in space, we're talking about stories that unfold across billions of years. Galaxies and their black holes grow up together, like cosmic companions, eventually settling into a kind of mature, peaceful coexistence. Consider one of the most distant galaxies we can observe, home to one of the largest black holes we know about. The immense size of that black hole tells us a story about its past. This galaxy must have experienced numerous mergers, countless periods where gas rushed inward to feed the central monster. There would have been times when this system blazed so brightly it could be seen across most of the observable universe. As that black hole released enormous amounts of energy, it would have shaped everything around it. Star formation might have been pushed to different regions. Gas might have been heated and scattered. The entire balance of the galaxy gradually adjusted by this central presence. By studying these extreme systems and comparing them to galaxies with smaller black holes, astronomers can trace patterns. They look at how fast stars are forming, how much gas is available, how the overall structure differs. These comparisons help us understand the bigger picture of how galaxies change over cosmic time. There's something almost poetic about this whole arrangement. A galaxy contains hundreds of billions of stars. Each of those stars might have planets, might host its own complex story of formation and evolution. And at the center of this vast community of stars and worlds, there sits a region that can never be seen directly, that sends out no light of its own, that will never reveal what lies inside its boundaries. Yet this invisible region plays a starring role in the life of the entire system. It's a reminder that in the universe, the most important things are often the ones we cannot see. Influence and visibility don't always go together. We often think of importance in terms of what can be observed, what makes itself known. But cosmic evolution suggests a different kind of significance, one based on gravitational influence and long-term effects, rather than immediate visibility. To study these relationships, Astronomers use telescopes that see different types of light. Optical telescopes reveal the stars themselves. Radio telescopes can detect cold gas clouds. X-ray telescopes pick up the hot, energetic regions near active black holes. By layering these different views together, scientists build a complete picture of how matter moves through these systems and how energy flows from the center outward. This multi-layered approach becomes especially important when studying galaxies with active central black holes, where processes at the core can affect regions far from the center. It's similar to how we measure black holes in the first place, by looking at what they do rather than what they are. This theme runs throughout astronomy, and perhaps throughout human knowledge more generally. We learn about the unseen through careful observation of the seen. We understand invisible forces by watching how they move visible objects. The cosmic story continues across billions of years. When dew down, invisible appears. Stars are born in some regions while dying in others. Gas flows inward, toward the center, gets heated, sometimes gets pushed back out. Black holes grow during active periods, then settle into quieter phases. The entire system constantly reshapes itself. Through all these changes, that central region of darkness remains. Not as an empty space, not as an absence of something, but as a presence, a participant in the long, slow story of galactic evolution. When you really start thinking about time, it becomes clear that our everyday experience barely scratches the surface. We assume time flows the same way for everyone, everywhere, like some invisible current that carries us all forward together. But venture close enough to something truly massive, like one of those supermassive black holes sitting at the heart of distant galaxies, and this comfortable assumption falls apart completely. The thing about gravity is that we've been thinking about it wrong for centuries. Most people still picture it as some kind of invisible force, pulling things toward each other. You let go of a ball, it falls down. Simple as that. But gravity isn't really a pulling force at all. It's something far more subtle, far more strange. What we call gravity is actually the bending, the warping of space and time itself. Imagine space and time as a stretchy fabric, like a trampoline. When you place a heavy bowling ball in the center, it creates a dip, a curve in the surface. Now roll a marble nearby, and it doesn't travel in a straight line anymore. It follows the curved path created by that heavy ball. This is essentially what planets do around stars, what stars do around black holes. They're not being pulled, they're following the curves that massive objects create in the very fabric of reality. This warping doesn't just affect how things move through space, it affects time itself. The stronger the gravitational field, the more time slows down relative to areas with weaker gravity. Right here on Earth, this effect is tiny, almost negligible. A clock sitting at sea level runs just a fraction slower than one sitting on top of a mountain. The difference is so small you'd never notice it without extremely sensitive equipment. But it's there, measurable and real. Now scale this up to something with the mass of billions of suns, compressed into a region smaller than our solar system. The warping of space-time becomes extreme, dramatic, almost violent in its intensity. Time doesn't just slow down a little, it slows down so much that from far away, it appears to almost stop altogether. Picture this scenario. You're watching from a safe distance as something falls toward one of these monster black holes. As that object gets closer and closer to the point of no return, what scientists call the event horizon, time appears to crawl slower and slower from your perspective. The light coming from that falling object gets stretched out, shifted toward the red end of the spectrum, growing dimmer and dimmer. Eventually, from your viewpoint, the object seems to freeze at the very edge, suspended there forever, fading until it disappears from sight entirely. But here's where it gets really interesting. For the object itself, for anyone riding along on that journey, nothing strange happens at all. Their clocks tick normally, their hearts beat at the usual pace, their thoughts flow at the regular speed. They cross that boundary, that point of no return, without even noticing the moment it happens. Time, for them, continues as it always has. This reveals something profound about the nature of time itself. It's not universal, not shared equally among all observers. Time is local, personal, dependent on where you are and how you're moving. Near these supermassive black holes, this becomes incredibly pronounced, creating regions where time passes at vastly different rates, depending on your location. Consider a spacecraft drifting slowly toward one of these giants, equipped with the most precise atomic clock we can build. Far away, another observer watches with an equally precise timepiece. Initially, both clocks agree, ticking away in perfect synchronization. But as the spacecraft ventures deeper into the gravitational well, the clocks begin to diverge, first by tiny fractions of a second, then by seconds, then minutes, then hours. If that spacecraft could somehow hover just outside the event horizon, the difference would become staggering. A single day for the crew might correspond to months, or even years for the distant observer. It's not that the crew is moving in slow motion, it's that time itself is flowing differently for them compared to the rest of the universe. The black holes associated with distant quasars are particularly fascinating in this regard. These objects are so massive that their event horizons can stretch across distances comparable to planetary orbits. This creates vast regions of space where gravitational time dilation is significant, not just tiny zones near a point-like center. This has profound implications for how we understand these cosmic giants and their surroundings. The material swirling around in the accretion disk, that glowing, superheated matter spiraling inward, experiences this time dilation effect. From our distant perspective, processes happening near the black hole appear stretched out in time compared to how they're actually experienced locally. The gas and plasma in these accretion disks often move at incredible speeds, sometimes reaching significant fractions of the speed of light. This introduces another layer of time dilation, the kind predicted by special relativity. Near a black hole, both effects work together, gravity and motion, both conspiring to warp the flow of time in complex ways. When we observe the light from these distant quasars, we're seeing the combined effect of all these time dilations, all these warping effects. The radiation we detect has been stretched, modified by its journey through these extreme gravitational fields and high-speed environments. It makes you wonder about the nature of time itself, doesn't it? We tend to think of it as absolute, unchanging, the same for everyone, everywhere. But physics tells us otherwise. Time is malleable, flexible, intimately connected to matter and energy and motion. In the most extreme environments in the universe, near these supermassive black holes, time becomes almost like a landscape, with valleys where it flows slowly and peaks where it flows more quickly. This isn't just theoretical physics, it has practical implications too. The GPS satellites orbiting Earth have to account for gravitational time dilation, or they'd give you directions to the wrong location. The difference in gravitational field between the satellite's altitude and Earth's surface is tiny, but over time those tiny differences accumulate into significant errors. Scale that up to the vicinity of a supermassive black hole, and the effects become dramatic beyond imagination. Entire civilizations, if they somehow existed in such environments, could experience time at rates vastly different from the rest of the galaxy. Years could pass in the wider universe while only days tick by for them, or vice versa, depending on their exact location and trajectory. The more we learn about these extreme objects, the more we realize how much they challenge our intuitive understanding of space and time. They're not just gravitational monsters that devour everything nearby. They're laboratories for physics, places where the fundamental structure of reality becomes stretched and distorted in ways that reveal hidden truths about the universe itself. When astronomers peer through their telescopes at distant quasars, they're not just looking at bright lights in space. They're actually decoding messages that have been twisted and stretched by some of the most extreme physics in the universe. The light that reaches us carries fingerprints of time itself, being warped, frequency by frequency, like a cosmic barcode, written in the language of relativity. Picture this: the gas swirling around a supermassive black hole doesn't just glow, It experiences time at a completely different rate than we do here on Earth. From our perspective, watching from billions of light years away, processes in that churning disk appear to unfold in slow motion. But if you could somehow ride along with that gas, everything would feel perfectly normal. Collisions happening violently, temperatures soaring in what seems like an instant. This creates a strange puzzle for scientists. When they observe a sudden flare of brightness from one of these distant objects, they have to ask themselves, how long did that event actually last? The answer depends entirely on where you're standing, or rather, where you're floating in the curved fabric of spacetime. It's remarkable how gravity doesn't just pull objects toward each other, it literally changes the flow of time itself. Near a supermassive black hole, spacetime becomes so warped that the usual rules we're used to simply break down. The comfortable separation between space and time, something we take for granted in our daily lives, dissolves completely. Think about how we normally experience our world. We move through space, time passes, they feel like completely different things. But Einstein showed us that this intuition fails us in extreme environments. Space and time are actually two sides of the same coin, space-time, and when you bend one, you inevitably bend the other. This leads to some truly mind-bending scenarios. Imagine you could somehow find a stable orbit around a supermassive black hole, close enough to feel significant time dilation, but far enough away to avoid being torn apart. You could potentially experience years, well, decades, or even centuries pass for everyone else in the universe. It's like nature's own time machine, though admittedly, not a very practical one. The mathematics behind all this has been tested countless times, and every experiment confirms what general relativity predicts. Time dilation isn't just theoretical, it's happening all around us, though usually in amounts too tiny to notice without atomic clocks. Your head ages slightly faster than your feet, because it's a little further from Earth's gravitational field, though we're talking about differences measured in nanoseconds over a human lifetime. But near a black hole, these effects become impossible to ignore. The gravitational field is so intense that it dominates everything, bending light into impossible spirals, stretching time like taffy. Astronomers have learned to read these distortions like a book, using the patterns of warped light to measure how fast gas is moving and how strong the gravitational field really is. There's something almost poetic about using time dilation as a scientific tool. The very thing that makes black holes so mysterious, their ability to warp spacetime, also gives us a way to study them. It's as if the universe provides its own measuring stick, even in the most extreme places imaginable. This brings us to one of the most puzzling aspects of black holes: what happens at the event horizon itself. From the outside, it appears to be a frozen boundary where objects slow down and never quite seem to cross over. But from the perspective of something falling in, the horizon is just another point along the journey, crossed in a finite amount of time. These conflicting viewpoints challenge our most basic assumptions about reality. If two observers can have completely different, yet equally valid descriptions of the same event, what does that say about the nature of truth itself? Near a black hole, even the concept of now becomes ambiguous. Different observers disagree about what's happening when. This philosophical puzzle extends far beyond black holes. It touches on fundamental questions about whether time flows like a river or exists all at once, like a landscape. Does the universe have a single timeline, or are there as many timelines as there are observers? Black holes don't provide easy answers, but they certainly make these questions more urgent. When you consider that the largest black holes in the universe contain billions of times more mass than our Sun, the scale of these space-time distortions becomes staggering. These objects are like natural laboratories, testing the laws of physics under conditions we could never recreate on Earth. Every photon of light that escapes their gravitational grip carries information about the fundamental structure of reality itself. There's also something quietly profound about how this connects to our human experience of time. We often feel rushed by time's passage, days blending into weeks in an endless forward march. But knowing that time itself is flexible, that it can stretch and slow depending on gravity and motion, offers a different perspective on our daily rush. Of course, here on Earth's surface, gravitational time dilation is far too small to affect our personal experience. Your sense of time speeding up or slowing down has much more to do with attention, emotion, and memory than with relativistic effect. But there's something comforting about knowing that time is part of the physical world, subject to natural laws, rather than being some abstract, untouchable force. The gas and dust spiraling into a supermassive black hole experience this time, warping firsthand. From a distant viewpoint, their final moments appear drawn out, stretched across what seems like eternity. But in their own reference frame, events unfold at their natural pace, right up until the laws of physics as we know them reach their limits. This duality of perspectives is one reason why black holes remain so captivating. They force us to confront the idea that reality itself might be more subjective than we'd like to believe. Different observers don't just see different things, they experience different versions of space-time itself. Perhaps most remarkably, astronomers can account for all these relativistic effects when they build their models. They've learned to translate between what they observe through telescopes and what's actually happening in the local environment of the black hole. Time dilation has moved from being a theoretical curiosity to being a practical tool for understanding real astronomical data. The ultimate fate of matter that crosses the event horizon remains one of physics' greatest mysteries. We know that from the outside, objects appear to freeze at the horizon, their light growing dimmer and redder until it fades away completely. But what actually happens to that matter, from its own perspective, pushes our understanding of physics to its breaking point. In the end, studying supermassive black holes teaches us that time isn't just the stage where the cosmic drama plays out. Time is part of the performance itself, shaped by gravity, twisted by motion, and revealed most clearly in the presence of these extraordinary objects. They remind us that even our most basic assumptions about the universe, like the steady tick of time itself, might be more flexible than we ever imagined. Looking at the vastness of space, there's something deeply humbling about realizing that even our most extreme objects, these impossibly massive black holes, might not represent the end of the story. The universe has this curious way of constantly rewriting its own records, leaving us to wonder whether there's truly a ceiling to how large something can grow. Black holes don't exist in isolation, floating alone in empty space. They're part of a much larger, constantly moving system, where matter flows like rivers through cosmic landscapes. Space itself keeps expanding, structures form and dissolve, and everything influences everything else. It's a bit like watching a slow-motion dance that's been going on for billions of years. The growth of any black hole depends entirely on what's happening around it. These cosmic giants can only get bigger if there's something nearby to consume, whether that's clouds of gas, wandering stars, or even other black holes that venture too close. All of this food comes from the surrounding neighborhood, and that neighborhood is shaped by forces operating on scales we can barely imagine. In the early universe, conditions were remarkably different from what we see today. Galaxies were packed much closer together, like houses in a crowded city. Gas was abundant everywhere, swirling in thick clouds throughout space. Collisions between galaxies happened regularly, creating chaotic, busy environments where black holes had countless opportunities to grow fat and massive. As billions of years have passed, the universe has changed dramatically. Galaxies have drifted farther apart from each other, carried by the relentless expansion of space itself. Much of that abundant gas has either been consumed, forming new stars, or heated to such extreme temperatures that it refuses to collapse into anything. The overall pace of growth has slowed to a crawl compared to those early violent days. This shift suggests something profound about limits in nature. There might not be some fundamental law of physics that says a black hole cannot exceed a certain size. Instead, the practical constraints come from the changing environment around them. It's like trying to build a skyscraper when land and materials are plentiful. Construction is straightforward. But as resources become scarce and space gets crowded, each additional floor becomes more challenging to add. For black holes, the key resources are mass and time. The larger one becomes, the more material it needs to grow even bigger. Meanwhile, the universe keeps spreading everything out, making it increasingly difficult for that material to find its way to the black hole's hungry maw. It's a race against cosmic expansion, and expansion seems to be winning. There's a fascinating balance at work when black holes feed. As material spirals inward, it forms a glowing disk that can shine brighter than entire galaxies. This incredible brightness creates outward pressure, like a cosmic wind pushing against anything trying to fall in. If a black hole attempts to eat too quickly, this pressure can actually blow its food away, creating a natural speed limit for growth. This phenomenon reveals something beautiful about the universe's self-regulating mechanisms. There's an upper limit to how fast any black hole can grow under normal conditions, not because of some arbitrary rule, but because of the fundamental physics of matter and energy. Even at this maximum rate, growing to truly enormous sizes requires not just time, but a steady, reliable supply of material in a stable environment. The largest black holes we've discovered tend to live in the most massive galaxies, often sitting at the centers of enormous galaxy clusters. These are cosmic metropolises, where gravity has spent billions of years gathering incredible amounts of matter. Smaller galaxies fall in like tributaries joining a river, contributing their stars, gas, and central black holes to an ever-growing system. This connection between black hole size and cosmic structure hints at another kind of limit. If there's a maximum size for galaxy clusters, or a limit to how much matter can concentrate in one region of space, then that indirectly constrains how large black holes can become. They're fundamentally tied to the largest structures in the universe. Dark matter plays a curious role in this story. This invisible substance makes up most of the mass in galaxies and clusters, forming a kind of hidden framework that guides where ordinary matter collects. But dark matter behaves very differently from the gas and stars that black holes typically consume. It doesn't clump together easily, doesn't cool down and form disks, and tends to pass right through other structures without interacting much. This means that even in regions packed with dark matter, black hole growth still depends primarily on ordinary matter, the kind that can lose energy and spiral inward. As the universe ages and ordinary matter becomes increasingly locked up in long-lived stars, or spread out in hot, diffuse clouds, the available food supply for black holes continues to dwindle. There's also a feedback mechanism that creates its own kind of limit. As black holes grow larger and more active, they become incredibly influential in shaping their surroundings. The enormous amount of energy they release can heat up or completely expel gas from the central regions of their host galaxies. In extreme cases, a very active black hole can essentially starve itself by driving away its own food source. This creates a self-regulating cycle. The black hole grows and becomes more active, which pushes material away, leading to a quieter phase until more material slowly drifts back in. Over cosmic timescales, this can lead to a kind of equilibrium where the black hole and its galaxy settle into a stable relationship that naturally limits further rapid growth. Looking toward the far future raises even more intriguing questions. If the universe continues expanding and becoming more diffuse, as current observations suggest it will, then opportunities for black hole growth will keep declining. Galaxies will become increasingly isolated, mergers will become vanishingly rare, and gas will be scarce everywhere. In such a universe, the largest black holes that exist might simply persist, quietly slowly evaporating through Hawking radiation over incomprehensibly long time periods. But some cosmological models suggest other possibilities. If the expansion of the universe were to slow, or even reverse in the extremely distant future, matter could begin falling back together on large scales. In such a scenario, black holes might find themselves once again in environments rich with material and frequent mergers. This is highly speculative territory, depending on physics we don't fully understand yet. The ultimate limits on black hole growth may be intimately connected to the fate of the universe itself. Are we living in a cosmos that will expand forever, spreading matter thinner and thinner until everything goes cold and dark? Or might there be cycles of expansion and contraction, creating repeated opportunities for growth and merger? These questions touch on some of the deepest mysteries in cosmology. What's particularly striking is how this connects to broader questions about limits in nature. Every record we've ever measured has eventually been broken. Every largest or most extreme has turned out to be temporary. Yet there's something profound about approaching what might be fundamental boundaries. regions where the universe itself seems to say, this far and no farther. Perhaps the most honest answer is that we're still learning. The black holes we can observe today represent just a snapshot of cosmic history, captured in the light that happens to be reaching us now. There could be even more massive objects lurking in distant galaxies, their light still traveling toward us across billions of years of space. Or there might be entirely different kinds of objects we haven't discovered yet, operating according to physical principles we're only beginning to understand. The question of ultimate limits forces us to grapple with the nature of infinity itself. In mathematics, we can imagine objects of any size, but the physical universe seems to impose its own constraints. These constraints aren't arbitrary. They emerge from the deep structure of reality itself, from the way matter and energy and space and time all interact with each other. The massive black holes we detect today might just be the tip of something much larger. When we peer into space with our telescopes, we're really looking at a cosmic census, counting the giants we can actually spot. But there's something almost humbling about this process, because our instruments can only see so far, only detect certain wavelengths of light. Think about it this way. A black hole sitting quietly in space, not actively feeding, becomes nearly invisible to us. Without that bright glowing disk of material spiraling into it, we'd miss it completely. This means our current record holders, these titans weighing tens of billions of times more than our sun, they're probably the loud ones, the active ones, putting on a cosmic light show. The universe loves to hide things from us. Dust clouds can shroud entire regions, making them impossible to study properly. There are vast patches of sky we simply haven't surveyed yet. Cosmic blind spots where monsters might be lurking. Every time we build a better telescope, we find something that challenges what we thought we knew. Measuring these cosmic beasts brings its own complications. We can't just put a black hole on a scale. Instead, we watch how stars and gas move around them, how they bend light, how they influence their surroundings. At the extreme end of the mass scale, tiny errors in our observations can translate into uncertainties of several billion solar masses. Two black holes might seem vastly different in size, but when you factor in measurement uncertainty, they could actually be quite similar. This uncertainty adds a strange kind of poetry to the whole endeavor. We're not just discovering what's out there, we're also discovering the limits of what we can know. Our knowledge becomes a conversation between the universe and our ability to understand it. Now, physics itself doesn't seem to set any hard upper limit on black hole mass. Einstein's equations allow for black holes of virtually any size, from microscopic ones that might have formed in the early universe to galactic-scale monsters. But physics rarely works in isolation. When you start mixing general relativity with quantum mechanics and thermodynamics, interesting constraints begin to appear. Black holes aren't just cosmic vacuum cleaners that swallow everything forever. They have a kind of temperature, they possess entropy, they're connected to the universe in subtle ways. Stephen Hawking showed us that they should actually evaporate over time, releasing tiny amounts of radiation back into space. For the supermassive ones, this process is so slow, it's essentially meaningless on any timescale we can imagine. But in the far future, trillions of years from now, this slow leak might matter. This creates a different kind of limit, not on how big they can grow, but on how long they can exist. In that distant future, when stars have burned out and galaxies have faded to nothing, black holes might be the last major structures in the universe, slowly giving their mass back as faint whispers of energy. There's something almost melancholy about this perspective. Even the most massive black hole, this seemingly permanent feature of space, is actually temporary when viewed against the full sweep of cosmic time. The universe has a way of recycling everything, even its most extreme objects. When astronomers look at the population of black holes across different types of galaxies, they see a clear pattern. Lots of small ones, fewer medium-sized ones, and very few genuine giants. This distribution tells us something important. Building a truly enormous black hole requires an almost perfect storm of conditions. You need early formation, a rich environment full of material to consume, frequent mergers with other black holes, and billions of years of stability. The rarest black holes aren't just big by accident, They're the survivors of very specific and uncommon histories. This rarity acts as its own kind of natural limit. Even if physics allows for arbitrarily large black holes, the universe might not often provide the right circumstances for them to actually form. There's also an element of cosmic chance involved. Two black holes that start out nearly identical might follow completely different paths through history. Small differences in their environments, tiny variations in the timing of galactic mergers, can lead to vastly different outcomes. One might grow into a relatively modest, supermassive black hole, while the other becomes an ultramassive giant. This sensitivity to initial conditions means the population of black holes we observe today reflects a complex dance between physical laws and historical accident. Each massive black hole carries with it the story of its particular journey through cosmic time. In a way, asking whether anything might outgrow our current record holders is really asking whether there might be even more extraordinary stories out there. Stories that began under more favorable conditions, followed more unusual paths through the evolving universe. This possibility keeps astronomers searching because the universe has consistently surprised us. Objects and phenomena that seemed impossible often turn out to be real. The cosmos has a talent for operating at the very edges of what we think is possible. But here's something worth reflecting on. When we talk about finding the largest black hole, we're applying very human concepts to a universe that doesn't really care about our records and rankings. The cosmos doesn't keep score or try to impress anyone. It simply unfolds according to its laws and the conditions it finds itself in. From this perspective, whether we ever discover something that dwarfs our current champions matters less than what the search itself teaches us. Each measurement, each new detection, helps us understand how matter and gravity and time interact on the grandest possible scales. It's not really about finding the winner. It's about mapping the territory of what's possible in our universe. The word largest isn't a destination. It's a moving target, a snapshot of our current understanding. The universe continues to evolve, continues to surprise us, continues to offer new possibilities that exist just beyond the edge of what we currently know. The universe operates on a fascinating principle that reveals itself everywhere we look. When simple rules get applied consistently across enormous spans of time, they create results that seem almost impossible. It's like watching a single drop of water, following basic physics, eventually carve out the Grand Canyon. Gravity sits at the heart of this cosmic story, and it behaves in a uniquely persistent way. Most forces in nature have opposites that balance them out, positive and negative charges that cancel each other. But gravity doesn't work like that. There's no such thing as negative mass to counteract regular mass. Every single particle, every atom, every grain of dust adds to the total gravitational pull. This creates something remarkable. Once matter starts clumping together, even just a little bit, gravity makes that clumping stronger. Denser regions pull in more material, which makes them even denser, which increases their pull even more. It's a feedback loop that never stops, always building on itself. The early universe was spread out almost perfectly evenly, with only tiny, barely detectable variations in density. But those minuscule differences were enough. Over millions and billions of years, gravity transformed those small irregularities into galaxies, galaxy clusters, and the vast web-like structures that stretch across space. Within this same process, stars formed, lived their lives, and sometimes collapsed into black holes. The largest black holes aren't separate from this story, they're deeply embedded in it. They represent one of the most extreme outcomes of gravity's relentless tendency to gather and concentrate matter in one place. But there's another force at play that makes things more interesting. The universe itself is expanding. Space stretches, carrying galaxies away from each other over time. This might seem like it would prevent large structures from forming, and on the biggest scales, it does. There are regions of the universe that will never interact, because space between them grows too quickly. On smaller, more local scales, though, gravity can overcome this expansion. Within galaxy clusters and groups, the mutual pull of matter stays strong enough to keep everything bound together. In these regions, matter continues falling inward, merging, building larger and larger systems. This creates a kind of cosmic landscape with incredible variety. Some areas become quiet and diffuse, while others become crowded and active. It's in these crowded regions, where matter has been drawn together over long periods, that the largest galaxies and black holes tend to form. Time plays a crucial role in allowing these extremes to exist. The universe is old, about 13 billion years. That number might sound abstract, but it represents an immense span of change and accumulation. Processes that would seem impossibly slow on human timescales become incredibly powerful when given billions of years to operate. A black hole doesn't need to grow quickly to become enormous, it just needs to grow steadily. A small amount of mass added year after year, century after century, million after million, eventually leads to something vast. The largest black holes aren't the result of single dramatic events. They're the outcome of countless small events layered on top of each other over cosmic time. Each star that falls in, each cloud of gas that spirals inward, each merger with another black hole adds another chapter to a very long story. In that sense, the universe allows extremes because it allows patience. It lets processes unfold without built-in endpoints or forced conclusions. The variety of environment across the universe creates another layer of opportunity. Not all regions of space are the same. Some areas are relatively empty, with galaxies scattered far apart. Others are dense, with hundreds or thousands of galaxies bound together in clusters. These different environments lead to very different evolutionary paths. In a quiet, isolated region, a galaxy might go through a fairly gentle life. It forms stars, uses up its gas, evolves slowly. Its central black hole may grow to a modest size, and then settle into a long, quiet phase. In a crowded cluster, the story becomes much more dynamic. Galaxies interact and merge. Gas gets stripped, heated, redistributed. Central regions become busy crossroads, where matter flows inward from many directions. These are the places where black holes can grow most dramatically, with access to steady supplies of material and frequent opportunities to merge with other black holes. The universe creates extremes of environment, rather than distributing matter evenly. It builds contrast into its own structure, and those contrasts lead to a wide range of outcomes. There's something profound about how the same physical laws that allow atoms to form, stars to shine, and planets to orbit also allow black holes to exist and grow. Nothing in those laws draws a clear line saying that mass cannot be concentrated beyond a certain point. Instead, there are conditions and balances. Pressure can counter gravity, energy can push back against collapse. But if gravity becomes strong enough and other forces can't resist, then collapse continues. This is why black holes exist in the first place. They represent a regime where gravity overwhelms other forces. On larger scales, similar principles apply. Nothing in physics forbids a galaxy from becoming very large or a cluster from becoming very massive. The universe doesn't choose to make something enormous. It simply follows its rules. Sometimes those rules, when given enough room and time, lead to outcomes that feel extraordinary to the minds observing them. We're witnessing the natural results of simple principles operating patiently across vast distances and stretches of time, creating structures that sit at the very edge of what seems possible. The cosmos operates without sharp boundaries, without rigid limits that dictate exactly what can and cannot exist. This flexibility creates a universe that feels remarkably diverse, where structures span enormous ranges of size and mass. We find tiny, dim, dwarf galaxies alongside massive elliptical giants. We discover modest black holes orbiting near monster black holes, millions of times more massive. The universe doesn't push everything toward one uniform result. It allows for this incredible spectrum of outcomes. Think about how randomness shaped everything we see today. The early universe wasn't perfectly smooth, like a still pond. Instead, it contained tiny fluctuations in density, small ripples that probably came from processes happening in those first moments after the Big Bang. These fluctuations followed certain patterns, but within those patterns They were essentially random, like static on an old radio. Gravity took these barely perceptible differences and amplified them over billions of years. Places that started out just slightly denser than their surroundings eventually became the birthplaces of galaxies and galaxy clusters. Areas that were slightly less dense became the vast empty regions we call cosmic voids. Today's universe carries an imprint of those ancient, almost invisible variations. The biggest black holes we observe might owe their existence partly to being born in exactly the right location within that primordial pattern. This brings an element of chance into the cosmic story. Not everything about universal extremes follows simple, predictable rules. Some outcomes depend heavily on timing and location within a complex, evolving system. Here's something that might seem backwards at first. Extremes often play stabilizing roles. This shows up across different areas of science. In galaxies, a supermassive central black hole can actually regulate how gas flows and how quickly new stars form. During its active phases, it releases tremendous energy that prevents the galaxy from forming stars too rapidly. Without this regulation, galaxies might burn through their gas supplies too quickly, leading to chaotic, unbalanced evolution. On even larger scales, massive galaxy clusters help organize the motion of surrounding matter, contributing to the overall architecture of what astronomers call the cosmic web. From this perspective, the largest black holes aren't just extreme outliers sitting at the edge of possibility. They're integral parts of a system of checks and balances that influences cosmic evolution. The universe doesn't need them in any purposeful way, but their existence is woven into the broader dynamics of how structure develops. There's also a thermodynamic way to think about this. The universe tends towards states of higher entropy, which measures disorder or the number of ways a system can arrange itself. Black holes possess extraordinarily high entropy. For any given amount of mass, a black hole contains more entropy than almost any other object imaginable. This has led physicists to view black holes as natural endpoints for concentrating matter and information. They represent extreme states in the universe's tendency to explore all possible configurations. From this angle, very large black holes aren't surprising anomalies. They're reflections of the universe's underlying drive towards states that maximize certain physical quantities under the constraints of natural laws. This represents deep, ongoing research that highlights how extremes can arise naturally as favored outcomes under specific conditions. When astronomers examine how black hole masses are distributed across the universe, they find a wide range rather than one dominant size. There are many small black holes, fewer medium ones, and very few giants at the high end. This type of distribution appears commonly in nature, showing up in earthquake magnitudes, stellar brightness, and even city populations. Such patterns typically emerge from systems where growth combines steady processes with occasional large random events. For black holes, the steady processes involve accretion, gradually consuming nearby material. The large random events are mergers, when black holes collide and combine. This combination naturally produces a few very large outcomes, alongside many smaller ones. It's another example of how extremes arise without requiring special rules. Consider how this shifts our understanding of what the universe allows. The cosmos doesn't allow extremes by granting permission. It allows them by not preventing them. Its laws are open-ended enough, its timescales long enough, its environments varied enough that diverse outcomes can emerge naturally. This openness makes the universe such a rich subject for study. It's not a tightly constrained system producing identical results everywhere, but rather a landscape of possibilities shaped by simple rules and complex histories. There's something profound in recognizing that the same universe capable of producing something as massive and dense as the largest black holes can also generate something as delicate and temporary as human consciousness. Both exist within identical physical laws. This can create a quiet sense of connection when contemplating cosmic extremes. You're not just thinking about distant objects, you're considering the full range of what's possible within the reality you inhabit. This understanding influences how scientists approach their work. Knowing that extremes exist and can be even more extreme encourages astronomers to keep pushing beyond familiar territory. It motivates deeper surveys, more sensitive instruments, more ambitious theoretical models. The possibility that something even more extraordinary might await discovery provides powerful motivation for exploration. Studying extremes also helps refine our understanding of the laws governing everything else. When a theory successfully explains both ordinary and extraordinary phenomena, it gains credibility. When it fails at the extremes, it reveals where new ideas might be needed. The largest black holes serve not just as impressive objects, but as tests of our understanding, markers showing how far current theories can reach. The universe emerges not as a place of narrow constraints, but as a realm of broad possibilities, where fundamental rules, given sufficient space and time, unfold into outcomes that stretch the boundaries of imagination. The universe began its grand conversation billions of years ago, and certain voices in this cosmic dialogue carry much further than others. Black holes, especially the colossal ones sitting at galaxy centers, speaks through influence rather than sound or light. They whisper to stars, redirect the flow of gas, and quietly author the long stories of entire galaxies. Think about what a galaxy actually is for a moment. It's not some static painting hanging in space, but rather a living, breathing system that grows and changes over eons. Stars emerge from cold gas clouds, burn brightly for their allotted time, then die and scatter their remains back into the cosmic mix. Gas spirals inward, sometimes gets pushed back out, and the whole system reorganizes itself continuously. At the heart of many galaxies, the largest black holes act like cosmic thermostats, not controlling every detail, but certainly influencing the overall temperature of galactic life. When these central giants remain quiet, something beautiful happens. Gas can cool down, settle into dense pockets, and birth new generations of stars. Spiral arms light up with brilliant young clusters, creating those stunning galactic portraits we see in astronomy books. The galaxy takes on a vibrant, active personality, full of stellar birth and death cycles playing out across millions of years. But when the central black hole wakes up, the entire mood shifts. Material begins falling into its accretion disk, and the energy released becomes absolutely staggering. Radiation floods outward in all directions. High-speed jets of particles shoot along the black hole's rotational axis, like cosmic lighthouses. These outflows slam into surrounding gas, heating it up and sometimes blowing it clear out of the central regions entirely. Here's where it gets interesting from a philosophical standpoint. Hot gas simply refuses to collapse into new stars easily. If enough of a galaxy's gas gets heated or expelled, star formation can slow to a crawl, or even pause for incredibly long periods. It's like the galaxy goes into hibernation, waiting for conditions to improve. This creates what scientists call a feedback loop, though that clinical term barely captures the elegant dance taking place. The galaxy feeds material to its central black hole, and the black hole responds by releasing energy that determines how much material the galaxy can use for future star formation. Over cosmic timescales, this relationship helps set the entire pace of galactic evolution. In galaxies hosting the most massive black holes, this feedback becomes especially dramatic. The energies involved are so immense, they can influence gas, not just near the center, but across the entire galaxy, and even into the surrounding intergalactic space. Astronomers often find large bubbles or cavities carved out of the hot gas between galaxies, like cosmic soap bubbles blown by ancient black hole activity. Moving closer to the galactic center, the gravitational influence of these supermassive objects shapes stellar orbits in remarkable ways. Stars race through space at incredible velocities, following elongated paths that loop them close to the central region before flinging them back out again. It's like watching a cosmic version of Crack the Whip, with the black hole as the pivot point. Sometimes a star's orbit brings it fatally close. When this happens, the difference in gravitational pull between the star's near side and far side becomes so extreme that the star gets pulled apart like taffy. Scientists call this a tidal disruption event, which sounds rather clinical for what must be one of the most spectacular deaths in the universe. As the star stretches and tears, some of its material spirals into the black hole, forming a temporary accretion disk that can flare brightly enough to be seen across vast distances. These events are rare, but when they occur, they offer astronomers front-row seats to watch a black hole consume a star in real time. For the star, it's a dramatic finale to a billion-year journey through space. For the galaxy, it's just another small chapter in a much larger story. The broader stellar population tells its own tale about black hole influence. If the central giant suppresses star formation for extended periods, the galaxy becomes dominated by older, redder stars. These cooler, longer-lived stars give their host galaxy a more subdued, uniform appearance. Many massive elliptical galaxies at cluster centers display exactly this character, hosting some of the largest known black holes while maintaining relatively little ongoing star formation. Their stellar populations are ancient, their structures smooth and rounded, rather than rich with spiral features. In contrast, galaxies with smaller or quieter central black holes can continue forming stars for much longer periods, maintaining more varied and dynamic appearances. This connection between black hole activity and stellar populations helps astronomers link the small-scale physics of accretion disks to the large-scale appearance of entire galaxies. Stepping back even further, galaxies aren't scattered randomly through space like seeds thrown by a careless gardener. They're arranged in a vast cosmic web of filaments, clusters, and voids that emerged from tiny density variations in the early universe, amplified by gravity over billions of years. The largest black holes tend to occupy the densest parts of this network, sitting at the centers of the most massive galaxies, in the largest clusters. These regions represent cosmic crossroads, where matter has been flowing in from multiple directions for enormous spans of time. An ultramassive black hole becomes a kind of marker, indicating a particularly rich and active part of the cosmic web. It tells a story about where matter has accumulated and how the universe's large-scale structure has evolved over time. When astronomers study the biggest black holes, they're not just learning about those objects themselves. They're also learning about the environments that created them and about the history of structure formation on the grandest scales. It's like reading the universe's autobiography, written in the language of gravity and time. This brings us to a curious philosophical question about our own place in this vast story. At first glance, the connection between us and these distant giants might seem impossibly remote. The largest black holes are billions of light years away. Their gravity doesn't reach us, their activity doesn't affect our solar system, and our daily lives proceed completely untouched by their presence. Yet in a deeper sense, we're intimately connected to this cosmic drama. The elements that make up our bodies were forged in stars, stars that lived and died within galaxies shaped by central black holes. The very structure of the universe that allowed galaxies to form in the first place created the conditions where both we and these gravitational monsters could come into existence. There's something humbling about realizing that the same fundamental forces shaping galactic evolution over billions of years also govern the chemistry of life on a small rocky planet. We are, in a very real sense, participants in the same cosmic conversation that began when the universe was young, even if our voices are much quieter than those of the giants at galaxy centers. The elements that compose every part of your body, from the calcium in your bones to the iron in your blood, were created inside ancient stars that burned out billions of years ago. These stellar furnaces operated long before our sun even began to form. What's fascinating is that those same ancient stars existed within galaxies that were themselves being sculpted by enormous black holes at their centers. This creates a chain of cosmic events that stretches across unimaginable spans of time. The supermassive black holes that dominated the early universe influenced how galaxies took shape. Those galaxies became the nurseries where stars were born and died, and those dying stars scattered the heavy elements that would eventually become the building blocks of planets and life itself. When we study the most extreme objects in the universe, we're actually testing how well our theories work. The mathematics that describes how gravity behaves near a black hole is the same mathematics that explains more ordinary situations. Time moves slower in strong gravitational fields, and this effect shows up near black holes in dramatic ways. But the same principle, on a much smaller scale, has to be accounted for in GPS satellites orbiting Earth. Without correcting for these tiny time differences, your navigation system would be off by miles. So the abstract physics of black holes connects directly to the technology in your pocket. The universe operates on the same fundamental rules, whether we're talking about the most massive objects known, or the practical tools of daily life. Throughout human history, people have gazed upward and wondered what lies beyond the visible. Ancient astronomers tracked the movements of planets and stars, often weaving what they saw into elaborate mythologies. Over centuries, those stories gradually transformed into precise measurements and mathematical theories. Today's astronomers, studying black holes that outweigh billions of suns, are continuing this same tradition of curiosity. There's something remarkable about a species that evolved on one small rocky world, developing the ability to understand objects scattered across billions of light years. We're not outside observers looking in at the universe. We're part of the same cosmic story, made from the same kinds of atoms, following the same physical laws. Our capacity to think about these gravitational giants is itself a product of the long sequence of events that include star formation, galaxy evolution, and yes, the growth of black holes. In science, when we say something has meaning, we usually mean it provides information about the system it belongs to. The largest black holes tell us about conditions in the very early universe. They reveal details about how galaxies assembled themselves from primordial gas and dark matter. They show us what happens when matter gets concentrated on truly extreme scales. These objects also highlight the boundaries of our current understanding. Where our theories make accurate predictions, we gain confidence in our models. Where they struggle to explain observations, they point toward areas where new ideas might be needed. This makes supermassive black holes valuable not just as objects of study, but as guides for future research directions. Contemplating something that bends space and time itself can shift your perspective in subtle ways. It can make everyday worries feel smaller, at least temporarily. This doesn't diminish the importance of personal experiences. It simply places them within a much broader context, a reminder that our immediate world is part of something vastly larger. As telescopes become more sophisticated, astronomers will be able to observe black holes in unprecedented detail. They'll study the earliest quasars, which are galaxies powered by actively feeding supermassive black holes. They'll map how gas and stars move around these gravitational giants. They might even detect the ripples in space-time produced when two supermassive black holes spiral into each other and merge. Each new discovery adds layers to our understanding of how these objects interact with their environments. This process of exploration unfolds across generations of scientists, each building on the work of their predecessors. Sometimes new observations confirm existing ideas. Other times they force researchers to reconsider fundamental assumptions. The largest black holes, by pushing the limits of what seems possible, often trigger these moments of scientific revolution. Picture a galaxy viewed from far away. You might see elegant spiral arms, a bright glowing core, countless points of starlight arranged in beautiful patterns. But at the center of all that visible splendor, there's often something that can't be seen directly. Something that influences the entire structure, without ever appearing in photographs. The supermassive black hole shapes everything around it, while remaining hidden behind the event horizon. This serves as a reminder that not everything important is immediately visible. Some of the most influential components of any system work behind the scenes. The largest black holes aren't isolated oddities scattered randomly through space. They're integral parts of a connected network, linking the evolution of galaxies, the life cycles of stars, and the development of human knowledge into one continuous story of cosmic history. The universe carries within itself a kind of patience that stretches far beyond anything we can easily grasp. When we think about the future, we often picture dramatic changes, sudden shifts, moments when everything transforms at once. But the cosmos operates on a different schedule, entirely. One where the most profound changes happen, slowly, quietly, almost imperceptibly. Right now, as you listen to this, galaxies are still busy places. Stars are being born in clouds of gas and dust. Black holes are feeding on material that spirals into them, creating brilliant displays of light and energy. Galaxies crash into each other, merge, and reshape themselves. It's a universe full of activity, full of motion, full of the kind of cosmic drama that captures our imagination. But this busy period, this era of construction and growth, won't last forever. The universe has been expanding since its beginning, and that expansion is actually speeding up. Space itself grows larger, pushing galaxies apart from each other. The cosmic web, that vast network of matter that connects distant regions of space, stretches thinner and thinner. Think about what happens when you have a crowded room full of people, and then the room starts getting bigger while the number of people stays the same. Eventually, everyone becomes more isolated, more separated. Conversations become harder, interactions become rarer. That's essentially what's happening to our universe, but on a scale so vast that it takes billions upon billions of years to notice. The largest black holes, those massive objects that sit at the centers of galaxies, will witness this transformation firsthand. They've already lived through incredible changes. Many of them formed when the universe was much younger, much denser, much more active than it is today. They've grown by consuming stars, gas clouds, and even other black holes. Some have become so large that their mass equals billions of our suns. But in the distant future, these giants will find themselves in a very different environment. The galaxies they anchor will have used up most of their gas, the raw material needed to make new stars. The bright, hot, young stars that currently light up the night sky will have burned out. What remains will be mostly older, cooler, dimmer stars, the kind that burn their fuel very slowly and can last for trillions of years. Red dwarf stars, for instance, are so efficient with their nuclear fuel that they can shine for longer than the current age of the universe. But even they, eventually, will exhaust what they have. When that happens, galaxies will become much quieter places. Instead of the vibrant blues and whites of active star formation, we'll see mostly the dim red glow of dying stars and the faint light of stellar remnants. This period, which scientists sometimes call the degenerate era, will be dominated by what's left over after stars die. White dwarfs, which are the compressed cores of sun-like stars. Neutron stars, which are even denser, formed when massive stars collapse. And black holes, which represent the ultimate endpoint for the most massive stars of all. Among all these remnants, the largest black holes will be some of the most stable, most long-lasting objects in the universe. They'll outlive the stars that created them, the galaxies that house them, and most of the cosmic structures we see today. There's something almost poetic about this. The idea that objects born from stellar death become the longest-living inhabitants of the cosmos. But even black holes aren't truly eternal. According to our current understanding of physics, they slowly leak energy back into space through a process called Hawking radiation. It's named after Stephen Hawking, who first described how quantum effects near a black hole's event horizon can cause it to gradually lose mass. For small black holes, this process happens relatively quickly, though quickly in cosmic terms still means millions or billions of years. But for the largest black holes, the ones with masses billions of times greater than our Sun, the evaporation process takes an almost incomprehensible amount of time. We're talking about numbers with so many zeros that they lose all practical meaning. Timescales that make the current age of the universe seem like the blink of an eye. 10 to the power of 100 years. That's a 1 followed by 100 zeros. To put that in perspective, if you wrote out that number in normal-sized text, it would be longer than most sentences. And that's just an estimate for how long it might take a supermassive black hole to completely evaporate. During most of this incredibly long period, the black holes will exist in what we might call a state of cosmic solitude. The galaxies around them will have become much more isolated as the expansion of space carries distant neighbors beyond the reach of their gravitational influence. The night sky, if there were anyone around to observe it, would be mostly dark, with only the faintest glimmers of light from ancient stellar remnants. Occasionally, something might disturb this quiet. A wandering star might drift too close to one of these massive black holes and be torn apart, providing a brief flare of energy as the stellar material spirals inward. Or two galaxies, still bound together by gravity, despite the expansion of space, might finally complete a merger that began billions of years earlier, causing their central black holes to eventually spiral toward each other and combine. These black hole mergers would create ripples in space-time itself, gravitational waves that spread outward at the speed of light. In a universe where most other forms of energetic activity have faded away, such events might represent some of the last truly dramatic occurrences on a cosmic scale. The idea that black holes slowly evaporate introduces a fascinating twist to this story. For most of their existence, black holes are objects that accumulate matter and energy, growing larger and more massive over time. But in their final phase, they become sources of gradual release, slowly giving back to the universe everything they've collected over eons. This shift from accumulation to dispersal reflects a broader pattern in cosmic evolution. The early universe was hot, dense, and relatively uniform. Gravity caused matter to clump together, forming the first stars, galaxies, and black holes. But as the universe ages and expands, the overall trend moves toward greater isolation and eventual uniformity again, but at a much lower energy level. There's something deeply philosophical about this arc, this movement from concentration to dispersal. It suggests that even the most permanent-seeming structures in the universe are part of larger cycles, temporary patterns in an ongoing process of change. The largest black holes, despite their incredible mass and longevity, are not final destinations but way stations in a much longer journey. The silence of this future universe deserves special consideration. Sound, as we experience it, requires matter to carry vibrations through space. In a cosmos where matter has become extremely sparse, separated by vast regions of near emptiness, there would be very little medium for sound waves to travel through. The universe would become literally silent, with interactions between objects expressed not through sound, but through the slow, subtle influence of gravity and the even slower process of radiation. This silence isn't empty or meaningless, though. It's the silence of patience, of processes so gradual and long-term that they operate on entirely different timescales from anything in our experience. The largest black holes will exist within this silence, surrounded by enormous volumes of space containing almost nothing, occasionally interacting with whatever sparse matter remains in their vicinity. The timescales involved in these processes stretch our ability to comprehend them. We can write down the numbers, we can perform the calculations, but the experiential reality of such vast spans of time remains beyond our grasp. 1,000,000 years feels long to us. 1,000,000,000 years is almost unimaginable. But the time it takes for a supermassive black hole to evaporate makes even billions of years seem brief. Yet the same physical laws that govern these distant futures also operate in our everyday world. The quantum mechanics that predicts Hawking radiation also explains how electrons behave in atoms. The gravity that will eventually bring isolated black holes together also keeps the planets in their orbits around the Sun. There's a deep connection between the intimate and the cosmic, between the immediate and the eternal. This connection suggests that contemplating the far future of black holes isn't just an exercise in cosmic speculation. It's a way of understanding the fundamental principles that shape reality at every scale. The patient, gradual processes that will dominate the universe's distant future are already at work around us, but usually overshadowed by more immediate, more dramatic changes. The story of the largest black holes in the far future is ultimately a story about transformation. These objects, which began as the collapsed cores of massive stars, became the organizing centers of galaxies, the engines that regulated star formation and influenced the evolution of cosmic structure. In their final phase, they become agents of dispersal, slowly releasing their accumulated mass and energy back into the expanding universe. This transformation mirrors the universe's own journey from its hot, dense beginning toward its cold, sparse future. Black holes, especially the largest ones, serve as markers of this cosmic evolution, witnesses to changes that unfold over timescales so vast they challenge our understanding of permanence and change. There's also something humbling about this perspective. When we think about the quiet future of black holes, we're contemplating a time far beyond any human timescale, a period when the very concepts of civilization, biology, and perhaps even chemistry, as we know them, will have become irrelevant. Yet our ability to imagine and describe such futures represents one of the remarkable capabilities that have emerged during the universe's current, active phase. The thoughts you're having about these distant times and vast objects are themselves part of the universe's ongoing evolution, small but significant events in a much larger process of increasing complexity and understanding. This realization can bring a sense of perspective to both our immediate concerns and our long-term aspirations, reminding us that we are part of something much larger than ourselves, something that operates on scales of space and time, that dwarf our individual existence, that don't diminish its meaning. The atoms that make up your body right now were once burning inside stars that died billions of years ago. Those ancient stars collapsed, exploded, and scattered their contents across space. Eventually, that stellar dust found its way into new planets, new life, and ultimately, into you. This means you're not just observing the universe, you're literally made from it. When we look at the largest black holes in space, we're seeing the end result of gravity's patient work. Gravity never stops pulling, never takes a break. It gathered the first clouds of gas after the Big Bang, compressed them into stars, and when those stars ran out of fuel, it crushed them down into points of infinite density. Some black holes started small, maybe just a few times heavier than our sun. But over millions of years, they kept eating, growing larger and more powerful. The biggest black holes we know about weigh as much as billions of suns combined. That's a number so large it becomes almost meaningless to our everyday experience. Imagine trying to count to 1 billion, one number every second. You'd be counting for over 30 years without stopping. Now multiply that by the mass of something that could fit over 1 million Earths inside it. These cosmic giants don't just sit there quietly, they actively shape the galaxies around them. Gas spirals into them, heating up to millions of degrees, glowing brighter than entire star systems. The energy they release can push matter around for thousands of light years in every direction. They're like cosmic gardeners, deciding where new stars can form and where they can't. Light from these distant black holes takes billions of years to reach us. When you look at an image of a far galaxy, you're seeing it as it was when the universe was much younger. The light left its source when Earth was still forming, traveled through empty space all this time, just to end up hitting a telescope mirror and eventually reaching your eyes. Time itself behaves strangely near these massive objects. Einstein showed us that time isn't constant. It can stretch and compress depending on how strong gravity is. Near a black hole, time crawls by slowly compared to what we experience here on Earth. If you could somehow watch someone falling toward one of these giants, you'd see them moving slower and slower, their image growing redder and dimmer, until they seemed to freeze at the edge. But from their perspective, nothing unusual would happen. They'd fall normally, unaware that the rest of the universe was speeding up around them. This isn't science fiction, it's how reality actually works. Time is flexible, moldable, more like clay than concrete. Black holes also teach us about the limits of knowledge. There's a boundary around each one called the event horizon. Once anything crosses that line, no information about it can ever escape. It's not just that we can't see what happens inside, it's that the very concept of inside stops making sense in any way we can understand. We can calculate what the math tells us about these regions, but we can never observe them directly. This creates a fundamental edge to human understanding. There are things in the universe that will always remain mysterious, not because our technology isn't good enough, but because the universe itself has built-in limits on what can be known. The largest black holes will outlive everything else in the cosmos. Long after the last stars have burned out, long after planets have been stripped away by the expansion of space, these dark giants will still be there. They'll slowly evaporate through a process called Hawking radiation, but even that will take longer than we can really imagine. A black hole with the mass of our sun would take longer to evaporate than the current age of the universe, multiplied by itself trillions of times. The biggest ones will persist for so long that the number of years has more digits than there are atoms in the observable universe. In the far future, they'll be the last remaining structure, in an otherwise empty cosmos. This raises strange questions about the nature of existence itself. If consciousness requires complex chemistry, and complex chemistry requires stars and planets, what does it mean for these massive objects to persist in a universe where nothing else can think about them? They'll be monuments to a more active phase of cosmic history, witnesses to everything that came before. The study of black holes pushes physics to its breaking points. Our best theories, general relativity and quantum mechanics, give different answers about what happens at the center of these objects. One says matter collapses to an infinitely small point. The other says that's impossible. This conflict suggests we're missing something fundamental about how reality works. Scientists think the answer might involve understanding how space and time themselves emerge from something more basic. Maybe the smooth fabric of spacetime that Einstein described is like the surface of a calm lake, appearing continuous from a distance, but actually made up of tiny discrete parts when you look closely enough. The temperatures near black holes reach extremes we can barely comprehend. The gas spiraling into them heats up to hundreds of millions of degrees. At these temperatures, atoms break apart completely. Matter exists in states that don't occur naturally anywhere else in the universe. It's like having a laboratory for studying physics under the most extreme conditions possible. Yet, despite all this violence and energy, there's something almost peaceful about how black holes operate. They follow simple, elegant mathematical rules. Their behavior is predictable, orderly. They're not chaotic destroyers. They're more like cosmic vacuum cleaners, methodically processing whatever material comes too close. The largest ones grow very slowly now, compared to their early days. They've mostly eaten everything in their immediate neighborhoods. They'll continue to exist for eons, but much of their dramatic activity is behind them. In a sense, they represent the universe settling into a more mature, quieter phase. This long view of time changes how we might think about our own brief existence. We live in an era when stars are still forming, when planets can still develop complex chemistry, when the universe is still young enough for consciousness to emerge and contemplate itself. We're part of a temporary flowering, in an otherwise mostly empty cosmos. There's something both humbling and remarkable about that timing. We exist during the universe's most interesting chapter, when it's old enough to have developed complexity, but young enough to still be active and dynamic. The fact that we can think about black holes at all represents an incredible convergence of cosmic circumstances. The matter that makes up your brain was processed through multiple generations of stars, compressed in their cores, scattered by supernovas, reformed in new stellar systems. The calcium in your bones was made in stellar furnaces. The iron in your blood was forged in the heart of a dying star. You're not separate from these cosmic processes. You're a direct result of them. When we measure the universe's large-scale structure, we find that galaxies aren't scattered randomly through space. They form a web-like pattern, with long filaments connecting dense clusters. The biggest black holes sit at the intersections of these cosmic highways, where the most matter naturally accumulates over billions of years. This suggests that the universe has been organized from very early times by invisible scaffolding made of dark matter. We can't see this dark matter directly, but we can observe its gravitational effects. It seems to make up most of the matter in the universe, yet we barely understand what it is. The interplay between ordinary matter, dark matter, and the expansion of space itself creates the conditions where black holes can grow to their enormous sizes. It's a delicate balance that had to be just right for structure to form at all. If gravity was slightly weaker, matter would never clump together. If it was slightly stronger, everything would collapse too quickly for stars to shine. We find ourselves in a universe fine-tuned for complexity, where the fundamental constants allow for the slow construction of interesting structures over cosmic time. Whether this is a coincidence, a necessity, or something else entirely, remains one of the deepest questions we can ask. The largest black holes serve as anchors for some of the most beautiful objects in space. The galaxies that surround them contain hundreds of billions of stars, each potentially hosting planets, chemistry, maybe even other forms of life. These stellar cities rotate slowly around their dark centers, taking hundreds of millions of years to complete a single turn. Our own galaxy has a black hole at its center. Though it's relatively small compared to the giants we've been discussing, we can watch stars orbit around it, following elliptical paths that bring them incredibly close before slinging them back out into space. These observations confirm our theories about how gravity works in extreme environments. The universe continues to surprise us with new discoveries about these objects. We've now detected gravitational waves from black holes colliding and merging, ripples in space-time itself that carry information about events so violent they distort the very fabric of reality. We've taken pictures of the glowing gas around black holes, seeing their shadows silhouetted against the bright material falling into them. Each new observation adds another piece to our understanding, but also reveals new mysteries. The universe seems to be constructed in layers, with each level of investigation opening up deeper questions about the nature of existence, time, matter, and consciousness itself.